Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm glad you're here. Tonight, we're going to drift into a question so big, so quietly unsettling, that it has puzzled scientists and philosophers alike for centuries. What was there before the Big Bang? How can nothing exist? And is nothing even real? In this video, we'll explore the edges of time, space, and meaning. But before that, feel free to comment your time and location below. It's always amazing to see when and where we're all watching from, or gently drifting off. Also, the visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination do the floating. I would love and encourage you to watch the video till the end to learn many new things, but there is absolutely no problem if you doze off mid-way through the video. Let your thoughts float across the cosmos. A gentle request that, if you find comfort in these gentle explorations of science, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more sleepy minds and souls like us, who have an amazing curiosity and passion for science in their minds. It would help me reach 1,000 subscribers on this channel and support me for the time that goes into creating these long and beautiful videos daily on this channel. Let's begin. Welcome to a journey that began before time itself, before space had meaning, before the first star ever flickered to life in the cosmic darkness. Tonight, we're exploring one of the most profound questions humanity has ever dared to ask. What existed before the Big Bang? It's a question that pushes against the very boundaries of science, philosophy, and imagination, taking us to the edge of everything we think we know about reality. As you settle into this moment of quiet contemplation, perhaps with the gentle weight of evening settling around you, consider sharing where in the world you're listening from. There's something beautifully humbling about contemplating the universe's origins while scattered across our small planet, each of us under the same ancient sky that has witnessed every moment of cosmic history. The story we're about to explore challenges everything we typically think about beginnings and endings, about cause and effect, about the very nature of existence itself. Before we had galaxies, before we had stars, before we had atoms or even the fundamental forces that govern reality, there was something. Or perhaps, more mysteriously, there was nothing at all. But even nothing, as we'll discover, might be far more interesting than we ever imagined. Let's begin this gentle descent into the deepest mystery of all, where physics meets philosophy, and where our most sophisticated theories dissolve into wonder and uncertainty. This is the story of what came before everything, told with the reverence it deserves and the curiosity that drives us to ask impossible questions. The Big Bang Theory, that cornerstone of modern cosmology, tells us that our universe began approximately 13.8 billion years ago, in a moment of unimaginable density and temperature. In that first instant, everything we see around us today, every star, every galaxy, every particle of matter, was compressed into a point smaller than the period at the end of this sentence. Then, in what we call cosmic inflation, space itself began expanding faster than the speed of light, stretching and cooling until the fundamental forces we know today could take hold and begin their patient work of building complexity from simplicity. This is a story so well supported by evidence that it has become scientific orthodoxy. We can see the afterglow of that primordial fire in the cosmic microwave background radiation that bathes the entire universe. We can observe galaxies racing away from us in all directions, their light stretched red by the expansion of space itself. We can calculate the precise abundances of the lightest elements and find them matching exactly what the Big Bang Theory predicts. The evidence is overwhelming, elegant, and beautiful. But science, in its relentless pursuit of deeper understanding, cannot help but ask the next question. If the Big Bang was the beginning of everything, what caused it? What set the stage for that moment of infinite density and temperature? What existed before time and space themselves began their cosmic dance? These questions probe at the very heart of causality itself, challenging our most basic assumptions about how reality works. Traditional physics tells us that every effect has a cause, that nothing happens without something making it happen. Yet when we try to apply this principle to the Big Bang itself, we encounter a profound puzzle. How can we speak of causation before time existed? How can we imagine a cause without the framework of space and time in which causes typically operate? It's like trying to ask, what's north of the North Pole? A question that seems meaningful until you realize it's pushing beyond the boundaries of the concepts it employs. Some of the greatest minds in physics have grappled with this mystery, and their proposed answers are as varied as they are fascinating. Stephen Hawking, with his characteristic blend of mathematical rigor and poetic insight, suggested that asking what came before the Big Bang might be like asking what's south of the South Pole. Time itself, he argued, began with the Big Bang, making the question of before meaningless in any conventional sense. The universe, in this view, is not eternal, but has a definite beginning, and that beginning is not preceded by anything we could meaningfully call before. Yet this answer, elegant though it may be, doesn't satisfy everyone. Other physicists have proposed that our Big Bang might not have been the absolute beginning of everything, but rather one event in a much larger cosmic story. Perhaps our universe is just one bubble in an infinite cosmic foam, with new universes constantly being born through processes we're only beginning to imagine. Perhaps time itself has a more complex structure than we assume, looping back on itself or branching into dimensions we cannot perceive. The mathematics that describe these possibilities are mind-bendingly complex, involving concepts that stretch human intuition to its breaking point. We speak of extra dimensions curled up so tightly they're invisible to us, of quantum fluctuations that can spontaneously create space and time, of multiverses where every possible variation of physical laws plays out in infinite variety. These aren't the fantasies of science fiction, but serious scientific hypotheses proposed by researchers at the world's leading universities, backed by sophisticated mathematical frameworks, and, in some cases, by tentative observational evidence. One of the most intriguing possibilities is that the Big Bang emerged from what physicists call a quantum vacuum. Now, despite its name, a quantum vacuum is far from empty. It's a seething foam of virtual particles constantly appearing and disappearing, a realm where the normal rules of existence are suspended and the impossible becomes routine. In this strange landscape, energy can be borrowed from the future and paid back before anyone notices. Particles can tunnel through barriers they shouldn't be able to cross, and pairs of matter and antimatter can spontaneously appear from apparent nothingness. Perhaps some theorists suggest our entire universe is the result of one such quantum fluctuation, a cosmic accident that grew into everything we see around us. It's a humbling thought that all of human history, all of the Earth's magnificent biosphere, all of the countless stars and galaxies we observe, might have emerged from a random quantum event in a timeless, spaceless void. Yet the mathematics suggest this is not only possible, but perhaps inevitable, given enough time. Or rather, given the absence of time in which such fluctuations might occur. Another possibility that has captured the imagination of cosmologists is the idea of eternal inflation. According to this theory, the process that drove our universe's initial expansion might be ongoing elsewhere, constantly creating new regions of space-time that evolve into universes like our own. In this picture, the Big Bang wasn't a unique event, but one of countless such events occurring throughout a vast, perhaps infinite, superstructure that dwarfs our observable universe. Imagine a cosmic ocean where bubbles of space-time are constantly forming, each bubble containing its own Big Bang, its own evolution of matter and energy, its own potential for complexity and life. Our universe would be just one such bubble, finite in age but part of an eternal process of creation that has no beginning and will have no end. The implications are staggering. There might be universes where the fundamental constants of physics are slightly different, where stars form differently, where life takes forms we cannot imagine. There might be universes where consciousness never emerges, and others where it develops in ways that would seem magical to us. Some of these parallel universes might be remarkably similar to our own, differing only in minor details. Others might be so alien that we lack the concepts to describe them. The very notion of before becomes meaningless in such a context, replaced by an eternal now in which creation is always happening, always has been happening, always will be happening. But perhaps the most radical possibility of all is that the question of what came before the Big Bang is based on a fundamental misunderstanding of the nature of time itself. We experience time as a flowing river, carrying us from past through present toward future. We assume this experience reflects something fundamental about reality, that time has an objective direction and flow. Yet physics suggests a very different picture. Einstein's theory of relativity revealed that time is not absolute, but relative, stretching and compressing depending on gravity and motion. What we call now is not a universal moment, but depends entirely on our frame of reference. An event that is in the past for one observer might still be in the future for another. Time, rather than being a flowing river, might be more like a landscape, with past, present, and future all equally real, all existing simultaneously in what physicists call the block universe. If this view is correct, then the Big Bang is not something that happened in the past, but something that simply is, a boundary condition in the four-dimensional fabric of space-time. Asking what came before, it might be like asking what happens before the beginning of a movie. The question assumes a perspective outside the story, but if we're characters within the story, the beginning is simply where the narrative starts, not a moment preceded by other moments. These ideas push us to the very limits of human understanding, to regions where science and philosophy merge in contemplation of the deepest mysteries. We find ourselves confronting questions about the nature of existence itself. Why is there something rather than nothing? Why does the universe seem so perfectly calibrated for the emergence of complexity and consciousness? Are we alone in this vast cosmic drama, or are we part of something larger and more magnificent than we have yet dared to imagine? The search for answers to these questions drives some of humanity's most ambitious scientific endeavors. Particle accelerators probe the fundamental structure of matter, looking for clues about the conditions that existed in the first moments after the Big Bang. Space telescopes peer deeper and deeper into the cosmos, effectively looking backward in time to observe the universe as it was when it was young. Gravitational wave detectors listen for the echoes of cosmic events so violent they ripple the fabric of space-time itself. Each new discovery brings us closer to understanding our origins, yet also reveals new mysteries, new questions we hadn't even known to ask. We've learned that ordinary matter, the stuff of stars and planets and life, makes up only about 5% of the universe. The rest is dark matter and dark energy, substances that we can detect only through their gravitational effects, cosmic components whose nature remains almost entirely mysterious. Perhaps dark matter is made of particles that exist in dimensions we cannot perceive. Perhaps dark energy is the manifestation of quantum fluctuations occurring throughout empty space. Perhaps both are evidence of our universe's connection to other universes, other dimensions, other realms of existence that we're only beginning to suspect. The more we learn about the cosmos, the more we realize how much we don't know, how much mystery still surrounds us. As you drift deeper into contemplation, consider that you are part of this cosmic story, not just an observer, but a participant in the universe's ongoing evolution. The atoms in your body were forged in the hearts of ancient stars, scattered by stellar explosions, and gathered again by gravity into the remarkable arrangement that is you. You are a way for the cosmos to know itself, a temporary organization of matter and energy that has achieved the remarkable feat of consciousness, of self-awareness, of the ability to contemplate its own origins. The question of what came before the Big Bang might ultimately be unanswerable, at least in any conventional sense. But the very act of asking it, of pushing against the boundaries of knowledge and understanding, is part of what makes us human. We are the universe's way of wondering about itself, of reaching toward mysteries that might forever remain just beyond our grasp. Tonight, as you prepare for sleep, you can rest in the knowledge that you are part of something vast and ancient and ongoing. Whether our universe emerged from a quantum fluctuation, whether it's one bubble in an infinite foam of creation, whether time itself has a more complex structure than we imagine, you are here now, conscious and wondering, part of the most remarkable story ever told. The cosmos cradles you as it has cradled every generation of questioners and dreamers before you. Tomorrow will bring new discoveries, new questions, new opportunities to push further into the mystery. But for now, you can simply be present to the wonder of existence itself, to the miraculous fact that anything exists at all, to the beautiful possibility that consciousness can emerge from matter and contemplate its own impossible origins. Sweet dreams, fellow traveler in the cosmic story. The universe continues its ancient dance around you, and you are part of that dance, now and always, in this magnificent, mysterious, ever-unfolding tale of everything that is. The origin question. Let me pose a question that has haunted human consciousness since we first gazed up at the night sky. What came before the very first moment? What existed in the infinite silence before existence itself began to whisper into being? We stand at the edge of the ultimate mystery, peering into a darkness so profound that even darkness itself had not yet been born. You see, when we speak of the Big Bang, we often imagine it as some cosmic explosion bursting forth from nothing. But that's not quite right. The Big Bang wasn't an explosion in space. It was the birth of space itself. Time, matter, energy, the very fabric of reality all emerged from a singularity so dense, so impossibly compressed that our mathematics breaks down entirely when we try to describe it. But here's what keeps cosmologists awake at night. The Big Bang theory, for all its elegance and explanatory power, doesn't actually tell us what came before. It's like having a perfect recording of a symphony that begins at the first note, but tells us nothing about the composer, the silence that preceded the music, or the creative force that brought it into being. The evidence for the Big Bang is overwhelming. We can observe the cosmic microwave background radiation, the afterglow of creation itself, still echoing through the universe nearly 14 billion years later. We can measure how galaxies are racing away from us, carried by the expansion of space itself. We can calculate the precise ratios of hydrogen and helium that should have formed in those first crucial minutes, and find them exactly as predicted. Yet all of this evidence points to a beginning, not to what preceded that beginning. It's as if we're detectives who arrive at a crime scene to find a perfect set of clues about what happened after the event, but no trace of what led up to it. The universe appears to have emerged from a state so extreme that it erases all memory of what came before. This creates what philosophers call the problem of the first cause. If everything that exists must have a cause, then what caused the Big Bang? And if the Big Bang was the beginning of time itself, does it even make sense to ask what came before time? We find ourselves trapped in a linguistic paradox, using words like before and after that only have meaning within the framework of time itself. Some scientists have proposed that our universe emerged from quantum fluctuations in a pre-existing vacuum, but this just pushes the question back another step. Where did this quantum vacuum come from? What laws governed its behavior? The vacuum state that quantum mechanics describes is not nothing. It's a seething sea of virtual particles and fields, rich with potential energy, and governed by sophisticated mathematical relationships. Others suggest that time itself might be cyclical, that our Big Bang was not the beginning, but simply the latest in an infinite series of cosmic rebirths. Perhaps the universe expands and contracts in an eternal rhythm, each cycle erasing the memory of what came before. But even this elegant solution raises new questions. What mechanism drives this eternal cycle? What prevents it from running down like a cosmic clock? The most unsettling possibility is that the question itself may be meaningless. If time began with the Big Bang, then asking what came before is like asking what lies north of the North Pole. The question assumes a framework that doesn't exist. This isn't a failure of our knowledge, but a fundamental limitation of reality itself. Yet perhaps this limitation points to something profound about the nature of existence. In quantum mechanics, we've learned that uncertainty isn't just a product of our ignorance, it's woven into the very fabric of reality. Particles don't have definite positions and velocities until they're measured. Reality, at its deepest level, appears to be fundamentally probabilistic rather than deterministic. Could it be that existence itself emerged from this quantum indeterminacy? That the universe didn't need a cause in the traditional sense, but arose spontaneously from the quantum foam of possibility? This would mean that the deepest truth about reality is not some ultimate explanation, but rather the irreducible mystery of existence itself. The ancient Greek philosophers grappled with similar questions. Aristotle argued for an unmoved mover, a first cause that set everything in motion, but was itself uncaused. But this solution feels more like an intellectual placeholder than a genuine answer. It names the mystery without explaining it. Modern cosmology has revealed that the universe is far stranger than our ancestors imagined. Space itself is expanding, carrying galaxies away from each other like raisins in rising bread. Time passes differently in different gravitational fields. Matter and energy are interchangeable. The familiar world of our everyday experience is built upon a foundation of quantum uncertainty and relativistic paradox. Perhaps the question of what came before the Big Bang is teaching us something important about the limits of human understanding. We are pattern-seeking creatures, evolved to find causes and effects in a world of medium-sized objects moving at moderate speeds. But the origin of the universe operates according to laws that may be fundamentally alien to our intuitive understanding. This doesn't mean we should stop asking these questions. The very fact that we can conceive of the problem of cosmic origins, that we can push our understanding to the very edge of existence itself, is perhaps the most remarkable fact about human consciousness. We are arrangements of atoms that have somehow become aware of themselves and their place in the cosmic story. The mystery of what came before the Big Bang may ultimately be unanswerable, but it serves as a reminder of how much we still don't know about the nature of reality. It keeps us humble in the face of the vast unknown and fills us with wonder at the sheer improbability of our existence. As you drift towards sleep tonight, consider this. You are made of elements forged in the hearts of dying stars, arranged in patterns complex enough to contemplate their own origins. The atoms in your body have existed for billions of years, cycling through countless forms before finding their temporary home in your consciousness. You are the universe becoming aware of itself, a brief flowering of complexity in the vast garden of existence. The question of what came before may have no answer, but perhaps that's exactly as it should be. Some mysteries are meant to remain mysterious, not because they're beyond our understanding, but because they point to something deeper than understanding itself. In the end, the greatest truth may be that existence itself is the ultimate miracle, requiring no explanation beyond the simple, profound fact that it is. Yet even as these theoretical frameworks push the boundaries of our understanding, we must confront a humbling truth about the very nature of knowledge itself. When we probe the moments before the Big Bang, we are venturing into territory where our most fundamental assumptions about reality begin to break down. Time, space, causality, existence itself, all become fluid concepts that resist our attempts to pin them down with the precision we've grown accustomed to in other areas of science. Consider the profound implications of what we're attempting to understand. We are creatures who exist within time, whose every thought unfolds in sequence, whose very consciousness depends on the flow of moments from past to future. How then can we hope to comprehend a state of being that preceded time itself? It's like asking a fish to describe the experience of flying, or requesting that a two-dimensional being explain the nature of depth. We lack the conceptual vocabulary, the experiential framework, perhaps even the cognitive architecture necessary to truly grasp what it might mean for something to exist outside of time. This limitation extends beyond mere philosophical musing. In physics, we routinely encounter phenomena that challenge our intuitive understanding of reality. Quantum mechanics taught us that particles can exist in multiple states simultaneously until observed. Relativity showed us that time and space are not the fixed stage upon which events unfold, but dynamic participants in the cosmic drama. String theory suggests that the dimensions we perceive represent only a fraction of reality's true complexity. Each of these discoveries required us to expand our conceptual horizons, to accept that the universe operates according to principles that often defy common sense. The question of what preceded the Big Bang represents perhaps the ultimate test of this intellectual flexibility. Here, we encounter not just counterintuitive physics, but the possibility that our most basic categories of thought, cause and effect, before and after, something and nothing, may themselves be insufficient tools for understanding the deepest truths about existence. Some physicists have suggested that asking what came before the Big Bang is like asking what lies north of the North Pole. It's not that we lack sufficient data to answer the question, but that the question itself may be fundamentally meaningless. Time, in this view, is not an infinite river stretching back into the past, but more like a sphere with a definite boundary. Just as there is no point north of the North Pole because north loses its meaning at that location, there may be no before prior to the Big Bang, because before only has meaning within the context of time itself. This perspective, while intellectually satisfying in some ways, leaves many of us with a profound sense of incompleteness. Our minds seem hardwired to seek origins, to trace every effect back to its cause, to find the beginning of every story. The idea that the universe might simply have emerged from nothing, or that the concept of emergence itself might be inappropriate when applied to the ultimate origin, feels unsatisfying at a deep, almost visceral level. Perhaps this dissatisfaction reflects something important about the nature of human consciousness and our relationship to existence. We are pattern-seeking creatures, storytellers by nature, always attempting to weave the disparate threads of experience into coherent narratives. The possibility that reality might not conform to narrative structure, that there might be no ultimate once upon a time, to discover challenges not just our scientific theories, but our fundamental sense of how things should be. Yet even as we acknowledge these limitations, the human drive to understand persists. Scientists continue to probe the cosmic microwave background for clues about the universe's earliest moments. Theoretical physicists develop ever more sophisticated models of quantum gravity, seeking to understand how the fundamental forces might have behaved in the extreme conditions that prevailed near the Big Bang. Cosmologists refine their understanding of inflation, dark matter, and dark energy, gradually painting a more complete picture of cosmic evolution. Each of these efforts represents an act of profound intellectual courage. To work at the frontiers of knowledge is to accept uncertainty as a constant companion, to build elaborate theoretical structures on foundations that may prove to be shifting sand. It requires a delicate balance between bold imagination and rigorous skepticism, between the confidence necessary to propose radical new ideas and the humility to abandon them when the evidence points in other directions. The scientists who dedicate their careers to understanding the universe's origins know that they may never find definitive answers to the deepest questions. They understand that each discovery typically raises more questions than it resolves, that the horizon of mystery recedes even as our knowledge advances. Yet they persist in their investigations, driven by a conviction that the attempt to understand is valuable in itself, regardless of whether ultimate understanding proves attainable. This persistence reflects something beautiful about the human condition. Faced with the vastness of cosmic mystery, with questions that may exceed our capacity to answer, we choose curiosity over resignation, wonder over cynicism. We construct telescopes to peer deeper into space and further back in time. We build particle accelerators to recreate the conditions that prevailed in the universe's first moments. We develop mathematical frameworks of breathtaking complexity to describe phenomena that no human will ever directly observe. In doing so, we participate in a grand conversation that stretches across generations and cultures. The questions that drive modern cosmology are not fundamentally different from those that inspired ancient philosophers and mythmakers. What is the nature of existence? How did everything begin? What is our place in the larger scheme of things? The tools we use to approach these questions have grown more sophisticated, our understanding more nuanced and empirically grounded, but the underlying human impulse remains unchanged. As we stand at the threshold of the Big Bang, peering into the ultimate mystery, we find ourselves confronting not just the limits of scientific knowledge, but the boundaries of human understanding itself. We discover that some questions may be unanswerable, not because they are too difficult, but because they transcend the very categories through which we attempt to make sense of reality. This realization need not lead to despair or intellectual paralysis. Instead, it can inspire a kind of cosmic humility, a recognition that mystery is not the enemy of knowledge, but its eternal companion. In acknowledging what we cannot know, we gain a deeper appreciation for what we can discover. In accepting that some questions may forever remain beyond our reach, we find renewed motivation to explore those territories where progress remains possible. The story of what came before the Big Bang may ultimately be a story about the nature of stories themselves, about the power and limitations of narrative as a tool for understanding reality. We are storytelling creatures living in a universe that may not conform to the structure of stories, seeking beginnings in a reality where the concept of beginning might not apply. Yet in this very seeking, we find something profound about what it means to be human. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own origins. In our questioning, our wondering, our persistent attempts to push beyond the boundaries of the known, we embody the cosmos, reaching towards self-understanding. Whether we will ever truly comprehend what preceded the Big Bang remains an open question. But in the asking, in the searching, in the endless human drive to understand, we touch something essential about our place in the grand cosmic story. We are not merely observers of the universe's unfolding narrative, but active participants in its ongoing attempt to know itself. The profound question of what existed before the Big Bang has led us through a remarkable journey of scientific discovery and philosophical contemplation. We've seen how the observable evidence, from the cosmic microwave background to the expansion of galaxies, paints a compelling picture of our universe's fiery birth approximately 13.8 billion years ago. Yet this very success creates a tantalizing puzzle. If science can trace the universe back to its first moments, why does the question of before remain so elusive? The answer lies not in any failure of scientific method, but in the fundamental nature of reality itself. As we approach that primordial moment, the very concepts we use to navigate existence, time, space, causation, begin to lose their familiar meaning. It's as if we're explorers who have reached the edge of a vast continent, only to discover that our maps and compasses no longer function in the territory beyond. This limitation isn't a flaw in our understanding. It's a feature of the universe's deepest architecture. Just as a fish cannot comprehend the concept of dry land while swimming in the ocean's depths, we may be fundamentally constrained by our existence within time and space when trying to conceive of their absence or origin. Our brains, evolved to navigate cause and effect in a temporal world, struggle with concepts that transcend these categories entirely. Yet, this boundary has not silenced scientific curiosity. Instead, it has opened new frontiers of exploration. Quantum mechanics suggests that reality at its most fundamental level operates according to principles that defy our everyday intuitions. The quantum vacuum, far from being empty, seethes with virtual particles that pop into existence and vanish in timeframes so brief they challenge our understanding of nothing. Perhaps our universe emerged from just such a quantum fluctuation, a cosmic accident that became everything we know. The concept of eternal inflation offers another perspective, suggesting that our Big Bang was merely one bubble in an infinite foam of expanding universes. In this view, the question of before becomes meaningless because inflation has been occurring eternally with no beginning and no end. Our universe would be just one room in an infinite cosmic hotel with new rooms constantly being created, but no first room to mark the beginning. String theory and its mathematical descendants propose even more exotic possibilities. They hint at dimensions beyond our familiar 3 of space and 1 of time, at brains colliding in higher dimensional spaces, at cyclic universes that expand and contract in eternal rhythms. These ideas stretch the boundaries of what we can test experimentally, pushing science toward the realm of mathematical philosophy. But perhaps the most profound insight comes from recognizing that the question itself may be fundamentally flawed. Einstein's relativity revealed that time is not the universal constant we once imagined, but a dimension woven together with space into the fabric of space-time. If time itself began with the Big Bang, then asking what came before is like asking what lies north of the North Pole, a question that contains its own impossibility. Some cosmologists have proposed that time might be cyclic rather than linear, or that it might have no boundary at all. In these models, the universe doesn't have a beginning in the conventional sense, but rather exists as a complete, self-contained entity, where the concept of before simply doesn't apply. It's a perspective that requires us to abandon our intuitive understanding of temporal sequence and embrace a more holistic view of existence. The multiverse hypothesis adds yet another layer of complexity to these considerations. If our universe is one of countless others, each with its own physical laws and constants, then the question of origins becomes even more intricate. What governs the birth of universes? What determines their properties? Are there meta-laws that operate across the multiverse? Or is even the concept of law itself an emergent property of individual cosmic bubbles? These questions push us toward the recognition that there may be aspects of reality that are forever beyond human comprehension, not because we lack the tools or intelligence to understand them, but because the very nature of these aspects transcends the categories through which conscious beings like ourselves must necessarily think. We are pattern-seeking creatures in a universe that may contain patterns beyond our ability to perceive or conceive. This limitation, however, need not be a source of despair. Instead, it can be a wellspring of wonder. The fact that the universe contains mysteries that may be eternally beyond our grasp speaks to its profound depth and richness. It reminds us that reality extends far beyond the boundaries of human knowledge and imagination. Moreover, the journey of exploration itself has value independent of its destination. In wrestling with these ultimate questions, we've developed quantum mechanics, relativity, particle physics, and cosmology. We've learned to see the universe as a dynamic, evolving entity rather than a static stage. We've discovered that the very atoms in our bodies were forged in the hearts of ancient stars, connecting us intimately to the cosmic story we're trying to understand. The question of what came before the Big Bang also illuminates something profound about the human condition. We are beings who emerged from the universe's own evolution, temporary arrangements of matter and energy that have somehow become capable of contemplating their own origins. In pondering what preceded our cosmic birth, we participate in the universe's journey towards self-awareness. This perspective transforms the apparent limitation of our knowledge into something almost mystical. We are not outside observers studying a foreign object. We are the universe studying itself. Every question we ask about cosmic origins is the cosmos inquiring into its own nature. Every theory we develop is reality attempting to understand itself through the medium of conscious beings. In this light, the inability to definitively answer what came before the Big Bang becomes less a failure and more a feature of our cosmic situation. We exist within the very system we're trying to understand, like characters in a story attempting to comprehend their author. The mystery may be not just unsolvable, but necessarily so, woven into the very fabric of what it means to be conscious beings in a mysterious universe. As we continue to push against these boundaries, developing new theories and more sensitive instruments, we may discover that the most profound truths about existence lie not in final answers, but in the perpetual dance between question and mystery. The universe may be structured in such a way that consciousness and mystery are eternal partners, each giving meaning to the other in an ongoing cosmic dialogue. The question of what preceded the Big Bang thus becomes not just a scientific puzzle, but a koan for the modern age, a paradox that illuminates the nature of knowledge, existence, and our place in the cosmic order. In embracing both our capacity to explore and the limits of that exploration, we find ourselves exactly where we belong, as wandering beings in a universe that perpetually exceeds our grasp, forever drawing us deeper into the mystery of existence itself. The grand cosmological paradox, time's infinite recursion. Yet even as we stand at this threshold of understanding, contemplating the vast machinery of cosmic evolution and the delicate dance of forces that brought us into being, we encounter perhaps the most humbling realization of all, the profound limits of human comprehension when faced with the infinite. The question of what preceded the Big Bang forces us to confront not merely the boundaries of scientific knowledge, but the very architecture of thought itself. Consider the peculiar nature of this inquiry. When we ask what came before the beginning, we reveal something fundamental about how consciousness navigates reality. We are creatures embedded within time, our every thought unfolding in sequence, our memories trailing behind us like cosmic background radiation from our own personal Big Bangs of awareness. To think beyond time's beginning requires us to step outside the very framework that makes thinking possible, like trying to see our own eyes without a mirror. The cosmological models we've explored, eternal inflation, cyclic universes, quantum foam, bubbling with spontaneous creation, each represents humanity's heroic attempt to extend the reach of reason beyond reason's natural domain. They are intellectual constructs of breathtaking elegance, mathematical poems written in the language of differential equations and field theory. Yet each model ultimately leads us to the same precipice, the recognition that our most sophisticated theories may be elaborate metaphors, beautiful but finite attempts to capture something that transcends the very categories of understanding we bring to bear upon it. In quantum mechanics, we've grown accustomed to the idea that observation shapes reality, that the act of measurement collapses wave functions and crystallizes possibilities into definite states. Perhaps the question of cosmic origins presents us with an analogous situation, but inverted. Here, reality shapes observation, constraining not just what we can know, but what can meaningfully be asked. The universe's beginning may represent not simply an event beyond our current understanding, but a horizon beyond which the very concept of causation loses its grip on meaning. This is not to suggest that we should abandon the quest for understanding. Science has repeatedly demonstrated its power to illuminate what once seemed forever shrouded in mystery. The cosmic microwave background, once merely theoretical, now provides exquisite detail about the universe's infancy. Gravitational waves predicted by Einstein's equations have become tools for exploring the most violent events in cosmic history. Dark matter and dark energy, though still mysterious, are yielding their secrets to increasingly sophisticated observations and theoretical frameworks. But the question of ultimate origins may belong to a different category entirely. It may be less like asking about the temperature of a distant star, difficult but ultimately tractable, and more like asking about the color of Wednesday or the weight of justice. The question itself may contain hidden assumptions that render it unanswerable, not because we lack sufficient data or computational power, but because it represents a fundamental category error in how we parse reality. Yet this limitation, rather than being a source of despair, opens onto something profound: the cultivation of what we might call cosmic humility. To acknowledge the boundaries of understanding is not to diminish human achievement, but to place it in proper perspective. We are remarkable beings, capable of tracing the evolution of stars, mapping the large-scale structure of the universe, and understanding our own origins as arrangements of stellar debris temporarily animated by the flow of energy and information. But we are also finite beings, embedded within the very system we seek to understand, like characters in a novel attempting to comprehend their author. This humility breeds wonder rather than resignation. When we recognize that the deepest questions may not have answers accessible to minds like ours, we begin to appreciate the extraordinary fact that we can ask such questions at all. The universe has evolved, through billions of years of cosmic evolution, arrangements of matter and energy capable of contemplating their own existence. We are the cosmos awakening to itself, however briefly and partially. The question of what preceded the Big Bang thus becomes not merely a scientific puzzle, but a koan, a meditation on the nature of existence itself. It invites us to consider not just the mechanics of cosmic evolution, but the mystery of being, the strange fact that there is something rather than nothing, that the universe exhibits the peculiar property of self-awareness through creatures like ourselves. In this light, our cosmological theories become less like definitive answers and more like finger-pointing at the moon, useful for directing attention, but not to be confused with the reality they indicate. The mathematical elegance of our models, the beauty of their symmetries, and the precision of their predictions may be less important as literal descriptions of reality than as expressions of the deep human need to find meaning and pattern in the face of the incomprehensible. Perhaps the greatest gift of cosmological inquiry is not the answers it provides, but the questions it opens. By pushing our understanding to its limits, we discover not just the boundaries of knowledge, but the boundless nature of mystery itself. We learn that the universe is not merely stranger than we imagine, but stranger than we can imagine, that our most sophisticated theories may be primitive sketches of a reality that transcends all possible theoretical frameworks. And in this recognition, we find not defeat, but liberation. Released from the burden of needing to understand everything, we can more fully appreciate the extraordinary privilege of understanding anything at all. We can savor the partial glimpses of cosmic truth that science provides, while remaining open to the vast mystery that surrounds and sustains all our knowing. The question of what came before the Big Bang may ultimately be unanswerable, because it probes the very foundations of existence itself, the ground from which all questions and answers emerge. Like the ancient symbol of the Ouroboros, the serpent eating its own tail, our inquiry curves back upon itself, revealing not a linear progression toward final answers, but a circular dance of wonder and mystery that has no beginning and no end. In this dance, we find our place not as masters of the universe, but as participants in its ongoing creative unfolding. We are temporary arrangements of cosmic matter that have learned to ask questions, to seek patterns, to marvel at the beauty and complexity of existence. Our theories and models, however sophisticated, are less important as final truths than as expressions of the universe's capacity for self-reflection, moments when the cosmos pauses to consider its own mystery through the evolved consciousness of beings like ourselves. The deepest cosmological questions may thus be less about the universe's past than about its present capacity for wonder, less about what happened before the beginning than about what it means that there are beings capable of contemplating such questions. We are the universe's way of experiencing awe, its method of marveling at its own existence, its technique for transforming mere matter into meaning. And perhaps in the end, this is answer enough. Not a solution to the mystery of existence, but a celebration of it. Not a final theory of everything, but a recognition that the most profound truths may be those that forever elude our grasp, yet forever inspire our quest to understand. This profound question about what existed before the Big Bang has driven scientists to develop increasingly sophisticated theories, each more fascinating than the last. Some propose that our universe emerged from quantum fluctuations in a primordial vacuum, where the very concepts of something and nothing lose their meaning at the quantum level. Here, virtual particles constantly pop into existence and annihilate each other, suggesting that even apparent emptiness seethes with potential energy. Other theories suggest we might be living in an eternal inflation scenario, where our Big Bang was just one of countless bubble universes forming within an ever-expanding cosmic foam. In this model, there was no single beginning, but rather an endless series of births and deaths of universes, each with its own physical laws and constants. Perhaps our universe is merely one note in an infinite symphony of creation. The concept of cyclic cosmology offers yet another perspective, proposing that the universe undergoes endless cycles of expansion and contraction. In this view, our Big Bang might have been preceded by a big crunch, where a previous universe collapsed in on itself before bouncing back into existence. Time itself becomes circular rather than linear, with each cycle potentially lasting trillions of years. Some physicists have ventured into even more speculative territory, suggesting that our universe might be a hologram projected from the surface of a higher dimensional black hole, or that we exist within a computer simulation run by some advanced civilization. These ideas, while seemingly fantastical, emerge from serious attempts to reconcile quantum mechanics with general relativity. The mathematics behind these theories often leads us to conclusions that challenge our most basic assumptions about reality. String theory, for instance, suggests that the fundamental building blocks of reality might be tiny vibrating strings existing in 11 dimensions, most of which are curled up so small we cannot perceive them. In this framework, our three-dimensional world is merely a shadow of a far more complex underlying structure. Perhaps the most humbling aspect of this question is that it forces us to confront the limitations of human understanding. We are creatures evolved to navigate a world of medium-sized objects moving at moderate speeds, yet we attempt to comprehend the infinite and the infinitesimal, the eternal and the instantaneous. Our brains, shaped by millions of years of evolution on an African savanna, now grapple with concepts that stretch the very fabric of logic. The very act of asking what came before the Big Bang might be like asking what lies north of the North Pole. If time itself began with the Big Bang, then the concept of before becomes meaningless. We find ourselves trapped in the grammar of causation, forever seeking a first cause in a universe that might have no beginning in any sense we can comprehend. Yet this apparent futility of our quest does not diminish its value. The journey toward understanding, even if we never reach our destination, transforms us in profound ways. Each theory we develop, each equation we solve, each observation we make adds another piece to the vast puzzle of existence. We are the universe's way of understanding itself, consciousness emerging from matter to contemplate its own origins. In wrestling with these ultimate questions, we discover something remarkable about the nature of wonder itself. The mystery of what came before the Big Bang is not a problem to be solved, but a gift to be cherished. It reminds us that reality is far stranger and more beautiful than our everyday experience suggests. In the face of such cosmic mystery, we find not despair, but exhilaration, not confusion, but clarity about what it means to be human in an incomprehensible universe. As we drift towards sleep, we can take comfort in knowing that we are part of something magnificent and mysterious. The atoms in our bodies were forged in the hearts of dying stars. The water in our cells has traveled through countless forms across billions of years, and the very thoughts we think emerge from the same fundamental forces that shaped the cosmos. We are not separate from the universe, but intimately connected to its deepest mysteries. The question of what came before the Big Bang will likely remain with us for generations to come, inspiring new theories, new experiments, and new ways of thinking about reality. Perhaps someday, we will develop the conceptual tools needed to peer behind the veil of creation itself. Or perhaps we will discover that some questions are meant to remain questions, eternal sources of wonder in a universe that delights in surprising us with its infinite creativity and boundless mystery. As our cosmic journey nears its conclusion, we find ourselves at perhaps the most profound realization of all. The questions we've been exploring about what existed before the Big Bang have led us to a humbling truth that permeates not just cosmology, but the very nature of human understanding itself. Throughout our exploration, we've encountered theories that stretch the imagination. We've considered the possibility that our universe emerged from quantum fluctuations in a timeless void, where virtual particles dance in and out of existence according to the strange rules of quantum mechanics. We've pondered eternal inflation, where our Big Bang was merely one bubble forming in an infinite cosmic foam, with countless other universes perpetually coming into being. We've examined cyclic models that suggest our universe might be just one breath in an eternal cosmic rhythm of expansion and contraction. Yet each of these theories, elegant and mathematically sophisticated as they may be, ultimately confronts the same fundamental barrier: They push the mystery back one step, but they cannot eliminate it entirely. If quantum fields gave birth to our universe, what gave birth to quantum fields? If eternal inflation explains our cosmic origins, what explains the mechanism of eternal inflation itself? If our universe is cyclic, what set the cycle in motion? This is where we must embrace what philosophers and scientists call epistemic humility. The recognition that there may be aspects of reality that lie forever beyond human comprehension. Just as a fish swimming in the ocean cannot easily conceive of the vast continents and sky above the water's surface, we may be fundamentally limited by our position within space-time itself. Consider this carefully. Every tool we have for understanding reality, every concept we use to make sense of existence, has evolved within this universe. Our mathematics, our logic, our very capacity for reason emerged from billions of years of evolution on a small planet orbiting an ordinary star. These tools have proven remarkably powerful for understanding the universe we inhabit, but they may simply be inadequate for grasping whatever transcendent reality gave birth to space and time itself. The question of what came before the Big Bang may be like asking what color is the number 7, or what does Thursday taste like. These questions are grammatically correct, but they commit what philosophers call a category error. They apply concepts from one domain to another where they simply don't belong. When we ask what came before time began, we're using the concept of before, which is itself a temporal concept. We're like someone trying to measure temperature with a ruler, or weigh sound with a scale. Einstein's theory of relativity revealed that space and time are not the fixed stage upon which cosmic drama unfolds, but rather active participants in that drama. Time itself can stretch and compress, speed up and slow down, depending on gravity and motion. At the moment of the Big Bang, both space and time came into existence together. To ask what came before may be as meaningless as asking what lies north of the North Pole. This limitation isn't a failure of human intelligence. It's a profound insight into the nature of existence itself. We are pattern-seeking creatures who have evolved to navigate a world of cause and effect, of before and after, of here and there. But the deepest questions about reality may transcend these familiar categories entirely. Some of the greatest minds in human history have recognized this boundary. The ancient philosopher Lao Tzu wrote that the Tao that can be spoken is not the eternal Tao. The mystic Meister Eckhart spoke of a God beyond God, a reality so fundamental that even our concept of divinity cannot capture it. The physicist Werner Heisenberg observed that what we observe is not nature itself, but nature exposed to our method of questioning. Even in our scientific age, we've discovered that reality is far stranger than our everyday experience suggests. Quantum mechanics reveals a world where particles can exist in multiple states simultaneously until observed, where the very act of measurement helps create the reality being measured, where effects can precede causes, and where information can travel instantaneously across vast distances. If the familiar world of our direct experience operates according to such bizarre principles, how much more mysterious must be the realm that gave birth to physics itself? This doesn't mean we should abandon the scientific quest to understand our cosmic origins. Each new theory, each fresh insight, each bold speculation adds another piece to the magnificent puzzle of existence. The search for understanding is itself one of the most beautiful expressions of what it means to be human. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own existence. But perhaps the deepest wisdom lies in learning to be comfortable with mystery. In recognizing that some questions may be more important for the asking than for the answering. The question of what came before the Big Bang may serve not as a problem to be solved, but as a pointer toward the ultimate mystery of existence itself. In the end, the fact that we can even formulate such questions is itself extraordinary. 13.8 billion years after the Big Bang, matter has organized itself into brains capable of pondering the origin of matter itself. Energy has become conscious enough to investigate the source of energy. Time has produced minds that can contemplate what preceded time. We are cosmic archaeologists, digging through layers of physical law and mathematical relationship, seeking clues about the ultimate nature of reality. But we are also participants in the very mystery we're trying to solve. We are not outside observers peering into the universe from some neutral vantage point. We are the universe peering into itself, using tools forged in stellar cores and minds shaped by billions of years of evolution. Perhaps this is enough. Perhaps the wonder itself is more important than the answers. Perhaps the capacity to ask such questions is a gift more precious than any solution we might discover. In a cosmos vast beyond imagination, ancient beyond measure, and mysterious beyond comprehension, we have been given the extraordinary privilege of consciousness, curiosity, and wonder. As you drift towards sleep tonight, carried on a small planet through the cosmic dark, remember that you are part of the greatest mystery of all. You are stardust that learned to dream, matter that became conscious, a brief arrangement of atoms that can contemplate infinity. The question of what came before the Big Bang may forever remain unanswered, but the fact that you can ask it connects you to something magnificent and eternal. In the quiet darkness, as your conscious mind releases its grip on the day's concerns, you join the cosmic dance that began with the first moment of time. You are both questioner and question, seeker and sought, a temporary eddy in the vast stream of existence that flows from mystery toward mystery. And in that flowing, in that eternal becoming, perhaps we find not answers, but something even more precious, our place in the grand, unknowable whole. Yet even as we grapple with these profound limitations of human understanding, we must acknowledge that our curiosity itself represents something remarkable about our place in the cosmos. The very fact that we can formulate questions about what preceded existence, that we can imagine scenarios beyond the reach of empirical verification, speaks to something extraordinary about consciousness emerging from the quantum foam of reality. We are, in essence, the universe attempting to understand itself, even when that understanding bumps against the boundaries of what can be known. This brings us to a humbling realization about the nature of inquiry itself. Perhaps the most honest answer to the question of what came before the Big Bang is not a definitive explanation, but rather an acknowledgement that some mysteries may forever exceed our grasp. This isn't a failure of science or philosophy, but rather a recognition of the profound depths of reality that stretch beyond our current conceptual frameworks. The universe appears to be far stranger and more complex than our evolved minds are equipped to fully comprehend. Consider the extraordinary journey that has brought us to this moment of questioning. From the first stirrings of matter and energy in the primordial darkness, through the formation of stars and galaxies, to the emergence of complex chemistry and eventually life itself, we represent an almost impossibly unlikely arrangement of atoms that has somehow learned to contemplate its own origins. The calcium in our bones was forged in the hearts of dying stars. The iron in our blood danced in stellar cores billions of years ago, and the hydrogen in our bodies has been on a cosmic journey since the universe's earliest moments. In this light, our inability to penetrate the mystery of what preceded the Big Bang becomes not a source of frustration, but rather a reminder of the profound wonder that surrounds us. We exist in a universe that is simultaneously intimate and vast, comprehensible and mysterious, knowable and ultimately elusive. The questions we ask about cosmic origins connect us to something larger than ourselves, to the great chain of inquiry that stretches back to the earliest humans who looked up at the night sky and wondered about their place in the cosmic order. The theories we've explored, from quantum fluctuations to eternal inflation, from cyclic cosmologies to higher dimensional frameworks, represent humanity's most sophisticated attempts to push beyond the boundaries of the knowable. Each theory offers insights into the possible nature of reality, even if none can provide definitive answers about what preceded our cosmic genesis. They remind us that the universe is far more subtle and complex than our everyday experience suggests, operating according to principles that challenge our most basic assumptions about existence, causality, and the nature of reality itself. Perhaps most importantly, these explorations reveal that the question of what came before the Big Bang is not merely an academic exercise, but a profound meditation on the nature of existence itself. When we ask what preceded the universe, we're really asking about the foundations of everything we know and experience. We're probing the deepest structures of reality, the ultimate ground of being from which all complexity and beauty emerges. The fact that we can even formulate such questions, that we can construct mathematical models of cosmic genesis and peer back through time to within moments of the universe's beginning, represents an extraordinary triumph of human consciousness. We are cosmic archaeologists, digging through layers of time and space to uncover the secrets of our origins. Even when we encounter mysteries that may be forever beyond our reach, the journey of discovery itself enriches our understanding of what it means to exist in this strange and wonderful cosmos. As we stand at the threshold of the unknowable, we might find comfort in the realization that mystery itself is not an obstacle to overcome, but rather an essential feature of a universe rich enough to give rise to consciousness, beauty, and wonder. The questions that lie beyond our current understanding serve as invitations to humility, reminding us that we are part of something far greater and more mysterious than we can fully comprehend. In the end, perhaps the most profound insight we can gain from exploring the question of what came before the Big Bang is not a definitive answer, but rather a deeper appreciation for the extraordinary nature of existence itself. We live in a universe that is simultaneously explicable and mysterious, governed by mathematical laws, yet full of wonder that exceeds our ability to capture in equations. This paradox, this tension between the known and the unknowable, may be the most fundamental characteristic of the reality we inhabit. The journey of inquiry that has brought us to this point, from ancient mythologies to modern cosmology, from philosophical speculation to mathematical precision, represents one of humanity's greatest adventures. Even as we acknowledge the limits of our understanding, we can celebrate the remarkable progress we've made in comprehending the universe's structure and evolution. The fact that we can trace the cosmic story back to within fractions of a second of the Big Bang itself represents an almost miraculous achievement of human intellect and imagination. As we continue to push against the boundaries of the knowable, developing new theories and technologies that might shed light on the deepest mysteries of existence, we carry with us the recognition that some questions may forever remain open. This openness, this acknowledgement of mystery at the heart of reality, may be not a limitation, but rather a gift, ensuring that the universe remains a source of wonder and inspiration for generations of curious minds yet to come. As we reach the final stretch of our cosmic journey, we find ourselves standing at the edge of perhaps the most profound mystery of all. The question that has haunted humanity since we first gazed up at the stars and wondered about our place in this vast, unfolding story. What came before the very beginning? What existed before existence itself began to exist? we've traveled together through 13.8 billion years of cosmic history. From the first tentative stirrings of matter and energy to the grand architecture of galaxies dancing through space, we've witnessed the birth of stars, the formation of elements, the slow accumulation of complexity that eventually gave rise to planets, life, and consciousness itself. Still, it offers a path, a way of visualizing a time before time, quantum tunneling from nothing. And then there's perhaps the boldest idea of all, that the universe came from nothing, not from empty space, not from a previous cosmos, but from an actual absence of space, time, matter, and energy. In quantum mechanics, particles can appear spontaneously from a vacuum through a process called quantum tunneling. Some physicists, like Alexander Vilenkin, have proposed that the universe itself could tunnel into existence from nothing. It sounds like magic, but in the strange world of quantum physics, the rules of logic shift. In this model, the universe is a closed system. The total energy is zero, because the positive energy of matter is exactly cancelled by the negative energy of gravity. If the universe costs nothing, then perhaps it doesn't need a cause. It simply is. A quantum fluctuation from non-being to being. But what triggered it? Why did it happen once and not endlessly? And what is nothing anyway? Even the void may have structure. And that leaves us wondering, can nothing ever truly exist? A wall we can't climb. Yet as of now, every theory about what came before the Big Bang, from bouncing universes to colliding brains, to tunneling from nothing, remains speculative. We have ideas, we have math, but we don't have proof. The earliest we can see, through observations like the cosmic microwave background, is about 380,000 years after the Big Bang. We've modelled the first seconds, milliseconds, even femtoseconds with physics. But the first Planck time, the first 10 to 43 seconds, remains a mystery wall. Until we develop a full theory of quantum gravity, that wall may remain. What if the question is wrong? Doesn't make sense. Just as before time is a contradiction, perhaps we need a new way of thinking. Maybe time is emergent, not fundamental. Maybe causality breaks down at the Planck scale. Maybe before is a human idea, one that doesn't apply to the birth of all existence. It's possible we'll never answer this question, but the beauty lies in asking it. As your eyes close and your mind softens, hold on to this wonder, that you live in a universe with a past so ancient, it may not even have a beginning, that science has reached into fractions of a second, yet still stares into the unknown, and that somewhere, perhaps in the silence beyond time, there waits an answer. In the next chapter, we'll leave the realm of theory and enter the timeline of structure. We'll see how the early universe formed the first atoms, stars, and galaxies. A slow, brilliant journey from simplicity to complexity, from hydrogen to human minds. Chapter 7. The Birth of Matter. The early universe was no place for structure, comfort, or form. It was chaos, raw energy stretched thin across a rapidly expanding void, so blisteringly hot that the idea of matter, as we understand it, didn't yet exist. There were no atoms, no stars, no planets, just a thick, glowing soup of fundamental particles colliding, annihilating, and reappearing in endless cycles. And yet, it was in this violence that the seeds of everything, including you and me, were born. In this chapter, we explore a transformation that sounds almost mythological in scale. How energy became matter, how chaos turned to order, how the first protons, neutrons, and electrons emerged from the fireball of creation, and how eventually they coalesced to become everything from galaxies to DNA. But to understand how the universe birthed matter, we have to rewind to a point just fractions of a second after the Big Bang. to the moment of symmetry breaking. The fall from symmetry. At the earliest moment, all the forces of nature were united. Gravity, electromagnetism, the strong force and the weak force were all just different flavors of the same fundamental interaction. This is known as a state of perfect symmetry, an elegant, unified field that theoretical physicists still struggle to describe mathematically. But symmetry is fragile. As the universe expanded and cooled, this perfect balance broke. First, gravity split off, becoming its own distinct force. Then, the strong nuclear force separated, followed by the electro-weak force splitting into the electromagnetic and weak nuclear forces. Each of these breaks unleashed vast amounts of energy, and with each stage, the nature of the universe became more complex and more familiar. What had once been a uniform sea of energy was now setting the stage for particles, real particles, the kind that would one day form everything. This process is known as baryogenesis, the moment where the universe began to favor matter over antimatter. Why does anything exist? One of the greatest unsolved mysteries in modern physics is this. If the Big Bang created equal amounts of matter and antimatter, why didn't they annihilate each other completely? Why is there something rather than nothing? When matter and antimatter meet, they obliterate each other in a flash of energy. And yet, for some unknown reason, the early universe seems to have had a slight bias, a tiny imbalance in favor of matter. For every billion pairs of matter and antimatter particles, there was one extra matter particle left over. It doesn't sound like much. But that tiny imbalance was enough to leave behind the entire observable universe. Every star, every galaxy, every atom in your body. How did this happen? Some theories point to CP violation, a subtle asymmetry in the laws of physics that treat matter and antimatter slightly differently, but we don't know for sure. The reason we exist, and antimatter doesn't, remains one of the deepest mysteries in cosmology. The quark era. Let's zoom in further. At around 10 to 12 seconds after the Big Bang, the universe was still unimaginably hot. Trillions of degrees. In this searing plasma, quarks roamed free, unbound by the rules that today hold them together inside protons and neutrons. Quarks are among the fundamental building blocks of matter, tiny particles that come in different flavors: up, down, strange, charm, top, and bottom. But they don't live alone. In the world we inhabit now, quarks are never found in isolation. They exist in triplets, like in protons and neutrons, or in quark-antiquark pairs called mesons. Back in the quark era, though, things were different. Quarks and gluons, the particles that glue quarks together, moved freely in a high-energy particle soup called a quark-gluon plasma. But as the universe cooled to below 2 trillion degrees Kelvin, something remarkable occurred. Confinement. Quarks began to bind together, forming the first protons and neutrons, collectively known as baryons. This was the dawn of what we call the Hadron Epoch. Now, the universe wasn't just energy and radiation anymore. It was building stable matter, the formation of nuclei. For the next few seconds, the universe was dominated by a thick fog of protons and neutrons, positively charged and neutral particles that were still too hot to settle into anything stable. But as temperatures continued to drop, these building blocks began to fuse. This fusion event is known as Big Bang nucleosynthesis, and it occurred roughly 3 minutes after the Big Bang. In a brief window lasting just a few minutes, the universe forged the first atomic nuclei, hydrogen, the simplest and most abundant element in the universe, helium, about 25% of the universe's mass, and trace amounts of deuterium, lithium, and beryllium. The conditions had to be just right, too hot, and nuclei would be torn apart by high-energy collisions. Too cool, and fusion wouldn't start. But for a golden few minutes, everything aligned. The universe behaved like a cosmic nuclear reactor, producing the raw ingredients that would one day light up the stars. But these nuclei were still bare. They didn't yet have electrons. That would come much later. For now, the universe remained a violent ocean of ionized plasma, glowing with heat, flooded with radiation, and expanding with every passing second. The Dark Ages begin. After nucleosynthesis, the universe entered a long, dark chapter. Literally. This is known as the Cosmic Dark Ages, a time when the universe had cooled enough that fusion had stopped, but not enough for atoms to form. Photons, particles of light, were constantly bouncing off free electrons, making the universe opaque and impossible for light to travel freely. No stars, no galaxies. Just darkness and silence, filled with glowing, invisible heat. This lasted for hundreds of thousands of years. And during this time, tiny imperfections, slight overdensities of matter left over from the earliest moments, began to grow under the pull of gravity. These imperfections would eventually collapse to form galaxies, stars, and planets. But for now, they were just whispers in the dark. A universe becoming transparent. Finally, at around 380,000 years after the Big Bang, the temperature of the universe cooled to around 3,000 Kelvin. Electrons, now moving slowly enough, began to combine with protons to form neutral hydrogen atoms. This moment is called recombination, and it changed everything. With electrons locked into atoms, photons no longer scattered. For the first time in cosmic history, light could travel freely. That light still exists. We can detect it today as the cosmic microwave background radiation, the oldest light in the universe, stretched into microwaves by billions of years of expansion. It's a fossil glow from a time before stars, etched across the entire sky. Every time you tune a television to static, a small fraction of that static is the afterglow of the Big Bang. The universe had finally become transparent. Matter had formed, and the stage was set for everything to come. A delicate balance. It's easy to overlook how precarious all of this was. If the universe had expanded even slightly faster, matter would never have clumped together. Galaxies wouldn't exist. If the strong nuclear force was slightly weaker, protons wouldn't bind into nuclei. Hydrogen would be the only element. No stars, no chemistry, no life. If the matter-antimatter asymmetry were just a bit different, the universe would be empty. We are here, on a blue speck orbiting an ordinary star, because the laws of physics danced in perfect tune during those first few minutes after the Big Bang. It is a balance so fine that some scientists wonder, is it coincidence or design? Is it the result of natural law or evidence that our universe is just one of many, a random roll in a multiversal lottery? We don't know. But what we do know is this: the birth of matter was not inevitable, it was miraculous. Chapter 8. Echoes of Creation. The Cosmic Microwave Background. The universe has a memory, not in the way we humans carry memory, in words, pictures, or stories, but in temperature, in radiation, in the most ancient signal ever discovered. A signal that has been traveling, uninterrupted, for nearly 14 billion years. It is the echo of the Big Bang itself, and it still surrounds us today. This chapter is about that echo. It's called the Cosmic Microwave Background, or CMB for short. It's faint, it's cold, it's invisible to the naked eye, but it's everywhere, through every corner of space. No matter where you point a radio telescope, you will find it. A gentle, persistent hum of energy, as if the cosmos itself is whispering a story from the very beginning. Let's begin by going back to a time before there was light. Roughly 380,000 years after the Big Bang, the universe was hot, dense, and filled with a plasma of protons, electrons, and photons, a kind of primordial soup. Photons, the particles of light, couldn't travel far without smashing into an electron. The universe was opaque, like trying to see through a thick fog with a flashlight. Light was trapped, constantly scattered and absorbed. There were no stars, no galaxies, just this high-energy, chaotic ocean of particles and radiation. But as the universe expanded, it cooled. Eventually, the temperature dropped low enough, about 3,000 Kelvin, for protons and electrons to combine and form neutral hydrogen atoms. And with that, the fog lifted. For the first time in cosmic history, light could travel freely. And that light, the first light, is still out there. It's the CMB, a kind of fossil glow from the moment the universe became transparent. A photograph, in a sense, of the universe when it was just a few 100,000 years old. Now here's the extraordinary part. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They weren't looking for cosmic echoes. They were trying to eliminate background noise in their antenna. But no matter what they did, the noise remained. It came from every direction, day or night, Earth-facing or space-facing. They even cleaned out bird droppings from the antenna, thinking it might help. It didn't. Eventually, they realized what they had stumbled upon. They were hearing the CMB, the afterglow of the Big Bang itself. Without intending to, they had discovered one of the most important pieces of evidence in all of cosmology. For this accidental but revolutionary finding, they received the Nobel Prize in Physics in 1978. The discovery of the CMB did more than just support the Big Bang theory. It transformed it from an elegant idea into a testable scientific model. A universe born in a fiery beginning would leave behind a trace. And this was that trace. But what's even more fascinating is how uniform the CMB is. If you were to look at the entire sky in microwaves, you'd see a nearly perfect glow, uniform to 1 part in 100,000. That level of smoothness is astonishing. It tells us that the early universe was almost perfectly homogeneous. The same everywhere. No preferred direction, no special spot, just smoothness. But not quite. Because when you look more closely, with more sensitive instruments, you begin to notice slight fluctuations, tiny variations in temperature, just fractions of a degree. These are called anisotropies. And they are crucial. These little wrinkles are the seeds of everything. In those slightly denser areas of the early universe, gravity began to gather matter. Over billions of years, those regions would collapse into the first stars, the first galaxies, the first cosmic structures. Without the wrinkles in the CMB, there would be no galaxies, no planets, no people. Think of the CMB as a baby photo of the cosmos, taken when it was just 380,000 years old. A snapshot that not only shows what the universe looked like back then, but hints at everything it would become. In the 1990s, a satellite called COBE, the Cosmic Background Explorer, mapped these temperature differences in the CMB with unprecedented precision. What it revealed stunned the scientific world. The fluctuations weren't random. They followed a very specific pattern, exactly the kind you'd expect from quantum fluctuations stretched across the cosmos by inflation. It was confirmation of theory, seen in the sky. After COBE came WMAP, the Wilkinson Microwave Anisotropy Probe, which refined the map even further. And then, in 2013, the Planck satellite gave us the most detailed map of the CMB to date. It allowed scientists to measure the age, composition, and curvature of the universe with extraordinary accuracy. 8 billion years old, that it's made of 5% normal matter, 27% dark matter, and 68% dark energy. That the universe is flat, geometrically flat, meaning parallel lines stay parallel forever. All of this from a whisper of heat left over from the dawn of time. But not all is perfectly understood. When scientists mapped the CMB, they found a strange anomaly, a region of the sky that appears colder than the rest. It's called the cold spot. Some researchers suggest it's a statistical fluke. Others think it might be evidence of a collision with another universe, a remnant of a multiverse. It's one of the many open questions in cosmology today. Then there's the axis of evil, a rather dramatic name for an odd alignment in the CMB data. It appears that certain large-scale fluctuations line up in a way that shouldn't happen if the universe is completely random and isotropic. Is it a coincidence, a data artifact, or something more profound? We don't know. And that's what makes it beautiful. The CMB is both an answer and a question. It tells us so much, but it also reminds us how much we have yet to understand. It's a quiet map of our origins, and perhaps a key to our future. You can't see it with your eyes, you can't feel it on your skin, but it's there, all around you. A gentle, cosmic whisper from a time when the universe first lit up. A reminder that the night sky isn't just dark, it's filled with memory, with echoes, with light that has never stopped traveling. And as we close our eyes and drift further into thought or sleep, let this chapter settle in like a distant hum, a pulse from the beginning of time, still resonating, still reaching, still unfolding, because the story of the universe is not finished. The background is still playing, and we are just starting to understand the tune. Chapter 9, Dark Matter, the invisible puzzle piece. Close your eyes and imagine the entire universe, the stars, the planets, the galaxies. Now imagine everything you've ever seen, touched, or studied is just the tip of the iceberg, because it turns out the matter that makes up you, me, the Earth, and even all the shining stars in the sky adds up to less than 5% of everything that exists. Let that sink in. The remaining 95% of the universe is made of something else, something we cannot see, something we cannot touch, but something that must be there, because without it, the universe simply doesn't work. This chapter is about one part of that hidden reality, a mysterious form of matter that neither emits nor reflects light, but reveals itself through gravity. We call it dark matter. The story of dark matter begins not with what we see, but with what we don't. In the early 20th century, astronomers began mapping galaxies and observing how they moved, and it didn't take long before the numbers stopped making sense. Galaxies rotate. Just like our solar system, where planets orbit the sun, stars within a galaxy orbit around its center. And if you were to chart the speed of those stars, you'd expect them to behave like planets, moving faster near the center where gravity is strongest and slower near the edges. But that's not what we see. When astronomers like Vera Rubin carefully measured the speeds of stars in galaxies in the 1970s, they discovered something strange. Stars on the outer edges were moving just as fast as those near the center, in some cases even faster. According to Newtonian physics, that shouldn't be possible. The stars should be flying off into space. The galaxies should be tearing themselves apart. And yet, they hold together. Something invisible must be providing the extra gravity, a hidden scaffolding holding galaxies together, a vast web of unseen matter. That something became known as dark matter. But what is it? That's where the mystery deepens. Because to this day, we still don't know exactly what dark matter is made of. We know what it's not. It's not ordinary matter. It's not atoms, protons, or electrons. It's not stars or planets. or even black holes, at least not enough of them to account for what we observe. Instead, it seems to be something entirely different, a new kind of particle, one that rarely, if ever, interacts with normal matter, except through gravity. Axions, sterile neutrinos, supersymmetric particles, but none have been definitively detected. Still, the evidence for dark matter keeps piling up. We see it in gravitational lensing, when the light from distant galaxies is bent by the gravity of massive objects between us and them. Sometimes the visible mass, the stars and gas, isn't nearly enough to explain the amount of bending. But when we include dark matter, the math works out. We see it in the large-scale structure of the universe, the cosmic web of galaxies that stretches across billions of light years. Computer simulations show that only with dark matter can you reproduce the filament-like patterns we see in the night sky. We see it in the cosmic microwave background. Tiny fluctuations in the CMB tell us how much matter existed in the early universe. And again, the numbers only make sense when dark matter is included. It is, in many ways, the invisible backbone of the universe. Without dark matter, galaxies would not form. Without dark matter, stars would not gather. Without dark matter, life as we know it would not exist. But for something so essential, it remains frustratingly elusive. Scientists have built massive underground detectors, deep beneath mountains or submerged in old mines, designed to catch the tiniest glimmer of a dark matter particle interacting with ordinary atoms. So far, none have succeeded. Space-based experiments like the Alpha Magnetic Spectrometer on the International Space Station scan the skies for clues. Particle colliders like CERN try to produce dark matter in high-energy collisions. But again, no confirmed signals yet. Some physicists have started to wonder, what if we're looking in the wrong place? What if dark matter isn't a particle at all, but a modification to gravity itself? An entirely new framework for how the universe works at large scales. These alternative ideas, like modified Newtonian dynamics, MOND, remain controversial, and while they can explain some galactic behavior, they often fall short when applied to the universe as a whole. The truth is, we're still in the dark, both literally and figuratively. But that darkness is not emptiness, it's not absence, it's not void. It is presence, silent, massive, fundamental. In fact, without dark matter, the universe we see today could never have emerged from the early chaos. In the immediate aftermath of the Big Bang, matter was spread nearly evenly, but small differences, small clumps, began to grow. And dark matter, through its gravitational pull, helped shape those clumps into the vast cosmic structures we now observe. Imagine it, giant clouds of invisible matter collapsing into filaments and halos, drawing regular matter toward them. Gas condensing, stars igniting, galaxies forming. Dark matter was the silent architect. And even now, it forms a kind of halo around every galaxy, including our own. The Milky Way is believed to be embedded in a dark matter sphere so vast and so massive that it outweighs all the visible stars many times over. You are moving through it right now. It's passing through your body, through your room, through the earth. And yet, it does so without a trace. Unless, someday soon, we catch it in the act. Scientists remain hopeful. New detectors are being built. New theories are being tested. The search continues. Not because we want the mystery to end, but because every discovery opens new doors. In the quiet of the universe, dark matter whispers secrets we have not yet learned to hear. But one day, perhaps, we will. And in that moment, we may come one step closer to truly understanding what the universe is made of. Chapter 10. The Rise of Galaxies, Building the Islands of the Cosmos. Close your eyes for a moment and imagine the night sky. not as we see it now, but as it once was. Imagine no stars, no glowing pinpricks scattered across the darkness, no moon, no Milky Way, no light at all. That was the universe for millions of years after the Big Bang, dark, silent, and filled with cooling hydrogen gas. It was a cosmos in waiting. But then something began to change. Gravity, patient and persistent, started pulling that gas together, tugging on it with invisible fingers. Denser regions grew denser still, like raindrops forming in clouds. And eventually, after nearly 400 million years of darkness, the first stars were born. This moment, the lighting of the first cosmic candles, marks the dawn of galaxies. This chapter is about how those galaxies formed, evolved, and came to shape the universe we now observe. The cosmic dark ages. Let's begin at the end of the cosmic microwave background, the moment the universe became transparent. After that point, the universe entered what we call the cosmic dark ages, a time when light existed but had nowhere to shine from. The hydrogen gas was too cool and too evenly spread out to form stars. The cosmos was quiet. But dark matter, the silent architect we met in the last chapter, was already at work. Invisible clumps of dark matter, called halos, began forming first. These acted like gravitational wells, pulling in the surrounding hydrogen and helium gas. Over time, these clouds of gas fell toward the center of these halos, compressed and heated up. Eventually, some of them reached a tipping point, and a spark ignited. The first stars, called population 3 stars, were likely massive, many times the size of our sun, and burned bright and hot. They didn't live long. Some may have lasted just a few million years before exploding in spectacular supernova. But in that brief time, they changed everything. They produced light. They forged heavier elements in their cores, carbon, oxygen, iron, and scattered them into the surrounding space. And they began the long process of transforming a simple, dark universe into a complex, luminous one. The birth of galaxies didn't form in a single event. They assembled over time, merging, colliding, growing. Initially, small protogalaxies emerged, small collections of stars bound by gravity. Over billions of years, these protogalaxies merged with others, forming the massive spiral and elliptical galaxies we see today. Gravity was the sculptor, and time was its chisel. The process of galaxy formation was chaotic. Collisions were frequent. But in space, collisions don't always mean destruction. Stars within galaxies are so far apart that even when two galaxies collide, their stars often pass by each other without touching. But their gas clouds and dark matter halos interact. Gravity pulls, tugs, and distorts. And from these interactions, new structures are born. In fact, many of the beautiful spiral galaxies we admire today were once the product of violent mergers. The arms of spirals may have been wound during these galactic dances. Even our own Milky Way is a product of this ancient chaos. It has cannibalized smaller galaxies in its past. And it's not finished. In about 4 billion years, it will collide with the Andromeda galaxy. The result won't be an explosion, but a transformation. The two galaxies will likely merge into a new, larger elliptical galaxy. Galaxies, in a sense, are always becoming. Types of galaxies. Today, we classify galaxies by shape and structure. Spiral galaxies, like our Milky Way, have swirling arms and bright central bulges. These arms are rich in gas and dust, where new stars are constantly forming. Elliptical galaxies are more rounded or elongated, with little structure. They contain older stars and less gas, which means they're not actively forming new stars. Irregular galaxies don't fit neatly into either category. Often chaotic in appearance, they may have been shaped by gravitational interactions or collisions. Each galaxy contains hundreds of billions of stars, and many of those stars have planets. So when we say that there are over 2 trillion galaxies in the observable universe, we're really talking about a nearly incomprehensible number of stars and worlds. It's not just a sky full of stars, it's a universe full of islands, each one possibly harboring the ingredients for life. Galactic evolution and feedback galaxies are not static. They change, evolve, and sometimes die. Star formation doesn't continue forever. It depends on the availability of gas, and as stars form, they consume that gas. In some galaxies, powerful feedback mechanisms, like supernova explosions or active black holes, can blow gas away, halting star formation altogether. Over time, some galaxies become red and dead, dominated by older, cooler stars, with no new ones being born. Others, especially those undergoing collisions, can become starburst galaxies, rapidly forming new stars at an explosive rate. These bursts can transform a galaxy's appearance, lighting it up with ultraviolet radiation and supernova. It's a cycle: birth, life, death, and rebirth, written across billions of light years. The role of black holes. In the center of nearly every galaxy lies a mystery: a supermassive black hole. These giants can weigh millions or even billions of times more than our Sun. We're not entirely sure how these black holes formed so early in the universe, but they seem to play a key role in galactic life. When material falls into a black hole, it doesn't just vanish. The matter heats up, accelerates, and often releases enormous amounts of energy in the form of radiation and jets. These active galactic nuclei can outshine the entire galaxy and influence the formation of stars by blowing away surrounding gas. In some ways, the black hole is the galaxy's engine room, unseen but deeply influential. Even now, the black hole at the center of the Milky Way, known as Sagittarius A, occasionally flares with X-rays and radio waves. It's quiet compared to others, but it reminds us that every galaxy carries a powerful secret at its heart. Observing the first galaxies. For a long time, astronomers could only guess at what the early galaxies looked like. The light from those distant times was too faint and too red-shifted to detect with clarity. But that changed with the launch of the James Webb Space Telescope, JWST, in 2021. Unlike its predecessor, the Hubble Space Telescope, JWST is optimized for infrared, perfect for observing the ancient stretched light from the first galaxies. Within months of becoming operational, JWST stunned the world. It captured images of galaxies that appeared just a few 100 million years after the Big Bang, some more structured and massive than expected. These early discoveries are forcing scientists to rethink their models of galaxy formation. How could such large galaxies exist so early? Did stars form faster than we thought? Was the universe more efficient in its youth? The truth is still unfolding. Every image from JWST is a new page in a cosmic diary, one written in light that has traveled for over 13 billion years. A universe still in bloom. Even today, galaxies are still forming. In distant regions of the universe, we can see galaxies merging, stars being born, and new structures taking shape. The universe may be expanding, but it's far from finished. And as we observe more, we begin to see patterns, not just of matter, but of meaning. We see how the same forces that shaped galaxies also shaped us. The elements forged in the first stars now make up our blood, our bones, and our breath. The story of galaxy formation is not just an astrophysical tale, it's a human one. Because without galaxies, there would be no stars. Without stars, no planets. And without planets, no life to look up and wonder how it all began. Chapter 11. The Mystery of Dark Energy. There's a silent presence out there. It doesn't shine. It doesn't emit or absorb light. It doesn't gather into stars or galaxies. And yet, it dominates the universe. We can't see it. We don't know what it is, but we know it's real because we can see what it does. This invisible something is called dark energy, and it makes up nearly 70% of the entire cosmos. To understand dark energy, we have to step back, far back, and look at the universe not as a static picture, but as something in motion. Because our universe is not just big, it's growing. And how it grows holds the key to one of the greatest mysteries in all of physics. Let's take a deep breath and step into that mystery together. The discovery of an expanding universe. For most of human history, people believed the universe was unchanging, a fixed backdrop to the events of our lives. But that changed in the early 20th century. In 1929, astronomer Edwin Hubble made a discovery that forever altered our understanding of the cosmos. He found that distant galaxies were moving away from us, and the farther they were, the faster they were receding. This wasn't because we were at the center of the universe. It was because space itself was expanding. Imagine dots on the surface of a balloon. As you blow air into it, the dots move away from each other, not because they're moving on their own, but because the space between them is stretching. That's what the universe is doing. And for decades, scientists believed that while the universe was expanding, the rate of that expansion must be slowing down over time. Gravity, after all, pulls things together. The more matter there is, the more gravity should work to decelerate the cosmic growth. But in the 1990s, something astonishing was discovered. A shocking acceleration. Two independent teams of astronomers were studying distant supernovae, exploding stars that act like cosmic mile markers. By comparing how bright these supernovae appeared to how far away they were, scientists could measure the expansion history of the universe. What they found shocked them. Instead of slowing down, the expansion of the universe was speeding up. It was as if some unknown force was pushing galaxies apart, overcoming the pull of gravity on the largest scales. This force, this unknown cause, was given a name, dark energy. But that name is really just a placeholder. It doesn't tell us what it is. It only tells us what it does. And what it does changes everything. What is dark energy? At its core, dark energy is a repulsive force. It seems to be woven into the fabric of space itself, causing space to expand faster and faster over time. But here's the strangest part. The more space you have, the more dark energy you get. That's because dark energy appears to have a constant density. As the universe expands and creates more space, it doesn't dilute, it stays the same. So with every new volume of space that appears, dark energy grows in total quantity. It's like a strange kind of fuel that never runs out, a cosmic pressure that accelerates the universe as it stretches. And we have no idea what it actually is. Some physicists think dark energy might be a form of energy related to the vacuum of space, an intrinsic energy that comes from quantum fields. Others suggest it might be a new type of field altogether, something that fills the universe but doesn't interact with ordinary matter. Still others propose that our theories of gravity might be incomplete. Maybe dark energy isn't a thing. Maybe it's a sign that we don't fully understand how gravity works on the cosmic scale. Each possibility raises profound questions, not just about physics, but about the nature of reality itself. Einstein's biggest blunder, or his greatest prediction. Interestingly, the idea of a cosmic repulsive force goes back even further than the 1990s. In 1917, Albert Einstein added a term to his equations of general relativity called the cosmological constant. This term acted like a kind of anti-gravity, a force that pushed space apart. Einstein wasn't trying to describe an expanding universe. In fact, he added the term to keep the universe static, because at the time, that's what everyone assumed it was. But in light of dark energy, That blunder looks more like a visionary insight. Today, the cosmological constant is one of the main candidates for what dark energy might be. A constant energy density that drives the acceleration of the universe. If that's true, then Einstein may have written down the equation for dark energy over 100 years ago. Measuring the invisible. If we can't see dark energy, how do we study it? Astronomers use a variety of methods to measure its effects. Type Ia supernovae help track how expansion has changed over time. Baryon acoustic oscillations, subtle patterns in the distribution of galaxies, give us a kind of cosmic ruler. Gravitational lensing reveals how matter, both dark and normal, bends light, indirectly helping map the influence of dark energy. The cosmic microwave background also provides clues about how the early universe's structure evolved under its influence. From all these lines of evidence, the picture is consistent. The universe is accelerating, and dark energy makes up about 68 to 70% of the total energy content of the cosmos. It's not just a footnote, it's the main chapter. A chilling future. The implications of dark energy go far beyond astronomy. They reshape our understanding of the past and point toward an unsettling vision of the future. If dark energy continues to dominate, the expansion of the universe will accelerate forever. Galaxies will drift farther and farther apart. Stars will burn out. Black holes will evaporate. Eventually, trillions of years from now, the universe could become a cold, dark, and empty place. A fate known as the Big Freeze. But that's only one possibility. If dark energy grows stronger over time, something called phantom energy, it could eventually overcome not just gravity, but all the fundamental forces. It might tear apart galaxies, stars, planets, even atoms themselves, in a final event called the Big Rip. Alternatively, if dark energy is temporary or evolves over time, the universe might one day slow down again and even contract, leading to a big crunch. The truth is, we don't know. The nature of dark energy holds the answer, and until we understand it, we're flying blind through the cosmos, tracing the outlines of a force that may decide the ultimate fate of everything. Searching for clues. All over the world, astronomers and physicists are racing to uncover the nature of dark energy. New observatories like the Vera C. Rubin Observatory and Euclid are designed to map billions of galaxies and study how cosmic structures evolved. At the same time, particle physicists are probing the quantum vacuum, trying to understand whether fluctuations in the fields of empty space might give rise to this mysterious force. But so far, no experiment has detected a dark energy particle. No telescope has resolved its true nature. It remains, for now, the deepest mystery in modern cosmology. And perhaps that's fitting. After all, the universe began in darkness, and perhaps, in some strange way, it will return to it. Not a darkness of ignorance, but of silence. A silence written across space and time by a force we're only just beginning to recognize. Chapter 12. The Multiverse. Hypothesis. Is this the only universe? What if everything we've ever known, our universe, our galaxies, our laws of physics, was just one version among countless others? What if there are other universes beyond the reach of our telescopes, where time flows differently, where gravity is weaker, or where stars never formed at all? It sounds like science fiction. But in modern cosmology, the idea of a multiverse, a vast collection of universes beyond our own, has emerged as a serious and deeply fascinating possibility. It's a theory born not from imagination, but from the edges of physics. And it's forcing scientists to confront the limits of what we can observe, what we can test, and what it means to understand reality itself. So in this chapter, we float beyond the bounds of what we can see and into the deep unknown to explore a question more profound than almost any other. Is this the only universe, or just one bubble in a cosmic sea? A finely tuned universe. Let's begin with something strange and undeniably real. Our universe appears to be finely tuned. Many of the constants in physics, the strength of gravity, the mass of the electron, the charge of the proton, the expansion rate of the universe, fall into very narrow ranges that allow stars, planets, and life to exist. Slight changes in these numbers would make our universe sterile or unstable, change the strength of the strong nuclear force, and atoms wouldn't hold together. Make gravity slightly stronger, and the universe would collapse. Make it slightly weaker, and galaxies would never form. Why do these numbers have the values they do? Some say it's coincidence, others suggest it's necessity, that only one kind of universe is possible. But another explanation has begun to gain traction. Maybe there are countless universes, each with different laws of physics, and we just happen to live in one where conditions allow life to emerge, because only in such a universe could anyone be around to ask the question. This is known as the anthropic principle, and it forms one of the philosophical foundations of multiverse theory. Cosmic inflation and bubble universes. Remember cosmic inflation from earlier chapters, the brief exponential expansion of space that occurred just after the Big Bang. One version of inflation theory, called eternal inflation, suggests that while our region of space stopped inflating and became a universe, other regions kept inflating and are still inflating today. Imagine space as a pot of boiling water. Each bubble that forms is a universe where inflation has ended and matter can form. But the pot itself, space, continues to boil, forever generating new bubbles. That's the bubble multiverse, a vast landscape of universes, each with potentially different properties, constants, and even dimensions. Our universe is just one bubble in an infinite foam. These other universes are completely disconnected from ours. No signal, no light, no information can pass between them. They are forever sealed from view, separate realities, with separate histories, but they might still be real. And inflation theory, backed by strong mathematical models and indirect evidence, points toward their existence. String theory and the landscape. Another path to the multiverse comes from string theory, a proposed framework for uniting quantum mechanics and gravity. In string theory, the fundamental building blocks of reality are not particles, but tiny vibrating strings. These strings can vibrate in different ways, and their vibrations determine the properties of particles. But for string theory to work, it requires extra dimensions, beyond the familiar 3 of space and 1 of time. These extra dimensions can be curled up or compactified in a vast number of possible ways. Each configuration leads to a different version of physics, different forces, different particles, different rules. In fact, the number of possible configurations is not just large, it's staggering. Some estimates suggest there are around 10,500 different possible universes allowed by string theory. This is known as the string theory landscape, an almost unimaginable number of potential realities. If each of these possible universes corresponds to a real universe somewhere in the multiverse, then the cosmos is far more diverse and strange than we've ever imagined. Quantum mechanics and many worlds. There's yet another road to the multiverse, one that starts not with cosmology, but with quantum mechanics. In the standard interpretation of quantum physics, particles exist in a superposition of states until they're observed, at which point they collapse into one definite outcome. But in the many worlds interpretation, collapse never happens. Instead, every possible outcome actually occurs, but in a separate, branching universe. Flip a quantum coin, and in one universe it lands heads, in another, tails. Every quantum decision, every measurement, every interaction causes the universe to branch. This creates a constantly multiplying set of parallel realities, a quantum multiverse where every possibility plays out somewhere. It's a bold idea, and while it avoids some of the paradoxes of quantum theory, it also introduces profound philosophical challenges. Are all these branches equally real? Can they ever interact? And if there are infinite versions of you living out different choices, what does that mean for identity or free will? The many worlds interpretation is elegant, consistent, and mathematically sound, but whether it reflects physical reality remains unknown. Can we ever test the multiverse? Here's the big question. If other universes exist, how would we know? After all, by definition, they lie beyond our observable universe. No light from them has reached us, and perhaps never will. But scientists have proposed a few intriguing possibilities. One is the idea of cosmic bruises. If our bubble universe ever collided with another, it might leave a detectable imprint in the cosmic microwave background, like a dent in the wall of space. So far, no definitive evidence of such a collision has been found, but the search continues. Another possibility is indirect support. If our theories, like inflation or string theory, predict a multiverse and also correctly explain things we can observe, that might lend credibility to the idea. In the end, the multiverse may be a framework we can only glimpse through mathematics and inference, not direct observation. And yet in physics, such ideas have often turned out to be real. Black holes were once purely theoretical. So was the expanding universe. So was time dilation. Maybe the multiverse too will one day become part of our accepted picture of reality. Philosophical and existential implications. The multiverse challenges more than physics. It challenges our sense of place. If there are infinite universes, are we insignificant, just one of many? Or is every universe, including ours, part of a grander structure we're only just beginning to grasp? Some worry that the multiverse makes science untestable. Others argue it's a natural extension of current theories, and may be necessary to explain the fine-tuning of our universe. It also changes how we think about meaning. If there are versions of you in other realities, living different lives, making different choices, does that diminish the life you're living now? Or does it highlight how precious it is? Because in this universe, this one, you are here, conscious, observing, wondering. That alone is extraordinary. One universe, or infinity. So where do we stand? The multiverse remains a hypothesis, intriguing, elegant, and provocative, but not yet proven. Still, its roots in inflation, quantum theory, and string theory give it serious scientific weight. And while we may never visit another universe, the very possibility forces us to expand our imagination and our understanding of what reality might be. It reminds us that the cosmos may be far larger, stranger, and more wondrous than anything we've dreamed, and that this universe, the one we call home, may be just one page in an infinite book of worlds. Chapter 13. The limits of the observable universe. What lies beyond? When you gaze into the night sky, you're not just looking into space, you're looking into time. The light from distant stars has taken years, centuries, even billions of years to reach your eyes. That light carries with it a story, a record of the past etched into the fabric of space-time. But here's the astonishing truth. There is a limit to how far we can see, a cosmic horizon, a boundary beyond which light has not yet had time to reach us since the beginning of the universe. This is what scientists call the observable universe. But it raises a profound question. What lies beyond that limit? Is it more of the same? Endless galaxies stretching into infinity? Is there an edge, a wall, a boundary? Or is there something fundamentally different waiting on the other side? A realm that defies the laws of physics as we know them. In this chapter, we stretch our minds and the very fabric of space to its outermost limits, to understand the edge of the knowable cosmos, and to wonder what lies beyond. What is the observable universe? Let's start with a basic but important distinction. The observable universe is not the entire universe. 8 billion years ago. 5 billion light years in every direction. That means the observable universe has a diameter of about 93 billion light years. Everything within that sphere is, in principle, observable. Galaxies, quasars, microwave background radiation. If light has had enough time to travel from them to us, they fall within our cosmic horizon. But beyond that sphere, light hasn't had time to reach us. Those regions are hidden, not because they don't exist, but because they're simply too far away. This is not a limitation of our instruments or our technology. It's a limitation imposed by the speed of light and the age of the universe. And it raises a fascinating implication. There could be vast regions of space, perhaps infinitely many, that we will never be able to observe, no matter how long we wait. The expanding universe and cosmic redshift. The reason for this limit lies in the expansion of space. Since the Big Bang, space itself has been stretching. Galaxies are not flying through space. Rather, space is expanding between them. This means that distant galaxies are moving away from us, and the farther away they are, the faster they appear to recede. This motion causes their light to be stretched, a phenomenon known as redshift. Just as the pitch of a siren drops when an ambulance moves away from you, light waves are stretched as objects recede, shifting their color toward the red end of the spectrum. Some galaxies are redshifted so much that their light has shifted completely out of the visible range. Others are redshifted to the point that the light will never reach us, even though it's already on its way. That's right. Some parts of the universe are receding from us faster than the speed of light due to the expansion of space. This doesn't violate relativity because it's not matter moving through space. It's space itself that's expanding, and that means some galaxies, some stars, some entire regions of the universe are forever out of reach. They are beyond the cosmic event horizon, a boundary beyond which events can never affect us. It's like watching a ship sail over the horizon on the ocean. You know it's still there, but you'll never see it again. Is there an edge to the universe? Now here's the real mind-bender. If there's an observable limit, does that mean there's an edge to the universe? Not exactly. According to the best current models, the universe is either infinite or so large and smoothly curved that it might as well be infinite for all practical purposes. There's no edge, no wall, no boundary you could reach in a spaceship. Instead, it's more like the surface of a balloon. You can travel in any direction forever and never hit an edge. You just loop around, although in 3D space, not 2D. But if that's the case, then our observable universe is just a tiny patch of a much grander structure. A speck on the surface of a cosmic balloon that may go on forever. We have no way of seeing beyond our horizon, but logic and mathematics suggest that the universe doesn't just stop there. It continues. How far? No one knows. And that leads us to a profound and unsettling truth. We may never know. The limits of knowledge. In science, we often believe that with enough time, technology, and ingenuity, we can understand anything. But the cosmic horizon suggests that some things may be fundamentally unknowable. There may be galaxies, thousands, millions, even billions of them, that will never send their light to us. There may be entire structures, clusters of galaxies, voids, and walls beyond our horizon. And there may be completely different regions of the universe where the laws of physics themselves are different. A consequence of the multiverse hypothesis we explored earlier. But we can't observe them. Not now, not ever. even the expansion of the universe is accelerating, driven by dark energy, meaning that the cosmic horizon is actually shrinking in terms of what we'll ever be able to see in the future. Galaxies currently visible to us will eventually redshift out of view. One day, all that may remain visible in our sky are the stars of our own galaxy and the fading glow of the cosmic microwave background. The rest of the universe, once visible, will become silent and dark. It's a sobering thought, and yet there's something beautiful in it too, because even in the face of these limits, we've come so far. From a small blue planet, using light, mathematics, and curiosity, we've mapped the shape of the cosmos. We've measured its age, its composition, and its structure. We've seen back nearly to the beginning of time, and we've asked questions no other species, as far as we know, has ever asked. Could we ever go beyond? It's tempting to imagine a future where we break the speed of light, where wormholes, warp drives, or some new physics allows us to escape the limits of the observable universe. But for now, these ideas remain speculative. Relativity tells us that no signal can travel faster than light in a vacuum, and quantum mechanics, while strange and non-local, doesn't offer a clear path around this rule. So unless some new discovery overturns our understanding of space and time, the cosmic horizon will remain a hard boundary, not just for observation, but for causality. We are confined to our island of space, watching a sky that is slowly fading. But maybe that's not a reason for despair. Maybe it's a reason to treasure what we can see, what we can know, and to continue exploring with wonder. Because even if we can't see everything, what we can see is already incredible. Billions of galaxies, trillions of stars, a universe that is vast, ancient, and beautiful beyond measure, and all of it visible from one tiny corner of space by creatures made of stardust who dare to ask what lies beyond. Chapter 14. Time before time. What came before the Big Bang? To say the universe began with the Big Bang is not controversial. It is widely accepted, well supported by observational evidence, and confirmed by the microwave background radiation that blankets the cosmos like a fossil echo of creation. But there is a question so profound, so quietly unsettling, that even the most seasoned cosmologists often tread carefully around it. What came before the Big Bang? It seems like a natural question. Everything we experience has a cause. Every event follows another. So surely the birth of the universe must have had something preceding it, a before, a prelude, a time before time. But this is where things become slippery. Because according to general relativity, the very theory that allowed us to rewind the expansion of the universe back to a singularity, time itself began at the Big Bang. And yet, the human mind resists that answer. We want more. We need to know. Was there something before everything? Was the Big Bang a true beginning, or just a transition? Let's begin to unfold this mystery. The problem with before. Our everyday understanding of time is linear. There is a past, a present, and a future. Events follow in sequence, governed by cause and effect. This model works perfectly well for most things in life. But the deeper we go into the foundations of reality, the more fragile this structure becomes. In Einstein's theory of general relativity, space and time are not separate entities. They are merged into a four-dimensional continuum called space-time. Massive objects like stars and black holes curve space-time, creating the force we experience as gravity. But time is just another coordinate, one that bends and warps along with space. Now consider this. If space-time itself began at the Big Bang, then there was no time before that moment, not because something existed eternally and then exploded, but because the very concept of before has no meaning outside space-time. From this perspective, the Big Bang wasn't an explosion in space. It was an explosion of space. There was no where for it to occur in, and no when either. In this framework, asking what came before the Big Bang is like asking what happened before time began. It's a category error, a question that dissolves under its own assumptions. And yet, science has never been comfortable resting on silence. So researchers began to ask a different question. Can we extend the timeline backward? Is there any mathematical or physical model that continues beyond t=0? The answer, surprisingly, may be yes. The singularity that wasn't. For a long time, the equations of general relativity seemed to predict a singularity at the beginning of the universe, a point of infinite density, infinite temperature, and zero volume. But infinities are not physical. They are a red flag that our equations have broken down, that we're pushing a theory beyond its domain of validity. And that's exactly what happens at the Planck scale, the unimaginably tiny interval of time, about 1043 seconds after the Big Bang, where quantum effects dominate. Here, quantum gravity is needed, a theory that merges general relativity with quantum mechanics. And because we don't yet have a complete theory of quantum gravity, we cannot say with certainty what happened at or before that moment. But scientists have proposed several bold ideas. One of the most intriguing is loop quantum cosmology, a branch of theoretical physics that applies the principles of loop quantum gravity to the entire universe. In this model, the Big Bang is not a singularity, but a bounce. The Big Bounce. According to loop quantum cosmology, the universe did not emerge from a point of nothingness. Instead, it existed before the Big Bang in a contracting phase. As the universe shrank, its density increased. But instead of collapsing into a singularity, quantum gravity effects caused a repulsive force at ultra-high densities. This force reversed the collapse and triggered a bounce into expansion. In this view, the Big Bang is not the beginning of time, but a transitional moment between contraction and expansion. There was a universe before our universe. Its properties, structure, and even its physics may have been different, but it had volume, energy, and time. And when it reached a critical density, it rebounded into the universe we inhabit today. This model offers a tantalizing glimpse of a cosmos with no beginning, only cycles. It also suggests that time stretches back before the Big Bang, not infinitely perhaps, but far enough to raise a new mystery. What happened in that previous universe? And are there traces of it still present in our own? Quantum foam and spontaneous universes. Another theory that attempts to address the before question involves the strange, seething chaos of quantum foam. In quantum mechanics, empty space is never truly empty. It is a storm of virtual particles, popping in and out of existence at unimaginable speed. Some physicists propose that in this frothing sea of quantum uncertainty, baby universes can spontaneously appear, tiny pockets of space-time that inflate and separate from the original vacuum. This is known as quantum cosmogenesis, the idea that universes are born spontaneously from fluctuations in a vacuum. If that's true, then our universe may have emerged from nothing, not in the philosophical sense, but from a quantum vacuum state governed by laws of physics. In this picture, there may be no before in a traditional sense. The universe began when a region of vacuum inflated, giving rise to space, time, and energy. But that inflation didn't happen in our space. It created its own dimension, its own arrow of time. In that case, asking what came before is like asking what's outside a bubble floating in another dimension. The question might still be meaningful, but not in a way we currently understand. The eternal inflation model. Another powerful theory is eternal inflation. According to this model, inflation, the brief, ultra-rapid expansion of the universe after the Big Bang, is not a one-time event. Instead, it continues eternally in some regions of space, creating an endless series of bubble universes. Each Big Bang is the birth of one such bubble, and each bubble may have its own laws of physics, its own constants, its own versions of matter and energy. Our universe is one bubble in a frothing, infinite foam of universes, a multiverse. In this view, the Big Bang is not the beginning, it's our beginning. And before the Big Bang simply means in the eternally inflating space-time that birthed our bubble. It's a deeply humbling idea, one that renders our entire observable universe a mere speck in a far grander reality. Philosophical implications. All these theories push the limits of physics, but they also push the limits of philosophy. If time began at the Big Bang, does that mean there was no causality before it? If the universe came from a quantum fluctuation, does that mean nothing can produce everything? If reality includes a multiverse, are we just one of countless versions of existence, with every possibility realized somewhere, even answerable? In the absence of data, we rely on mathematics, logic, and inference. But if we can never observe anything beyond the Big Bang, are we just constructing castles in the dark? Echoes of a pre-Big Bang past. Some scientists are searching for faint signatures of a time before time, patterns in the cosmic microwave background, or anomalies in the distribution of galaxies that might hint at events that preceded the Big Bang. One idea is that collisions between other universes, or bubbles, might have left scars on the sky. Another is that gravitational waves from a previous cycle of the universe could still be rippling through our cosmos. These signals, if detected, could be the first empirical evidence of a before, a ghostly fingerprint from an earlier reality. We haven't found such evidence yet, but we've only just begun to look, and if we do find it, the consequences would be staggering. It would mean we live in a universe with a memory, a history older than time itself, a universe without a beginning. Some philosophers and physicists have suggested that the very concept of a beginning may be flawed. Time may not be linear at all, but cyclical or emergent, a property that arises only under certain conditions. No ultimate origin, just an infinite regress of causes, or a self-contained loop, or a reality that simply is, with no beginning and no end. These ideas are speculative, but they remind us of an important truth. The Big Bang is not the end of the mystery. It is, in many ways, only the beginning. Chapter 15. The Invisible Thread. Dark Matter and the Hidden Architecture of the Universe. For most of human history, we believed that what we could see with our eyes, the stars, the sun, the moon, and the vast canopy of night, was all there was. Even as telescopes revealed more galaxies, more stars, more planets, it still seemed natural to think that light was the key to understanding the cosmos. If we could just gather more light, capture more photons, build bigger lenses, we'd reveal everything the universe had to show. But that assumption was wrong. Because in the late 20th century, astronomers began to realize that the visible universe, all the planets, stars, galaxies, nebulae, and radiation, made up only a tiny fraction of what was actually there. Something massive was missing. Something we couldn't see, couldn't touch, couldn't illuminate. It neither emitted light nor absorbed it. It passed through us and everything else silently. And yet, its influence was undeniable. It shaped galaxies. It bent the fabric of space. It anchored the cosmos together. This invisible thread, now known as dark matter, has become one of the greatest mysteries in modern science. And like so many questions in cosmology, It all begins with motion. Let's go back to the 1970s, to a scientist named Vera Rubin. She was studying the rotational speeds of galaxies, particularly the Andromeda Galaxy and others in our galactic neighborhood. According to Newtonian physics and everything we knew about gravity, the stars on the outer edges of a spiral galaxy should orbit slower than those closer to the center, where most of the visible mass, and therefore gravitational pull, is concentrated. But when Rubin measured those outer stars, she found something startling. They weren't slowing down at all. In fact, they were orbiting at the same speed as the inner stars. The galaxy was rotating like a solid disk, not like a whirlpool. This was not just a minor discrepancy. It was a violation of our understanding of gravitational dynamics, and the only explanation that made sense. There must be far more mass present than what we could see, a vast halo of invisible matter stretching beyond the galaxy's edges, exerting gravitational force to hold those fast-spinning stars in place. That was the birth of dark matter, not in theory, but in necessity. Rubin's work was met with skepticism at first, but more observations piled up. More galaxies showed the same behavior. Clusters of galaxies moved as if they were embedded in huge, unseen cocoons of mass. The evidence became overwhelming. Gravitational lensing, the bending of light from distant galaxies around invisible objects, provided more proof. Light from galaxies billions of light years away was being distorted and magnified in space, not by anything visible, but by the hidden gravity of something unseen. Dark matter was acting like a cosmic magnifying glass. So what is it? That's the problem. We still don't know. It doesn't clump into stars or planets. It doesn't emit or absorb radiation. It passes through ordinary matter and through itself, without friction or heat. It reveals itself only through gravity. According to current estimates, dark matter makes up about 27% of the universe. Compare that to the 5% of the universe made up of ordinary matter, everything we've ever touched, tasted, built, or burned. In other words, almost 85% of the universe's mass is invisible to us. Our galaxies, stars, and planets are like islands floating in a vast ocean of something else, something dark, ancient, and unknown. But that's not the end of the mystery, because in the late 1990s, astronomers made yet another discovery, one that would throw everything we knew, including dark matter, into further chaos. They were measuring how the universe was expanding. According to the Big Bang model, space has been expanding since the beginning, but gravity should be slowing that expansion down. Over billions of years, the pull of all the mass in the universe, including dark matter, should gradually decelerate the expansion, maybe even stop it altogether. But when two independent teams studied distant supernovae, exploding stars billions of light years away, they found something astonishing. The expansion of the universe wasn't slowing down, it was speeding up. This was completely unexpected. It was as if some unknown force was pushing the universe apart faster and faster, like an invisible hand at the edge of existence, accelerating everything outward. This force was called dark energy, another placeholder name for something we don't understand, and yet it accounts for nearly 68% of the total energy content of the universe. In other words, most of the universe is not only invisible, it's also accelerating. If that sounds strange, it should, because it means that everything we understand about the cosmos, from the shape of galaxies to the fate of the universe, is being governed by forces we do not yet comprehend. Let's recap the cosmic pie chart. Ordinary matter, 5%. Dark matter, 27%. Dark energy, 68%. You, your body, your room, your phone, the stars, the galaxies, all the atoms you've ever known, are made of just 5% of what exists. And we've only recently come to terms with this. It's like entering a cathedral in pitch darkness and trying to describe its architecture by touching a few columns near the door. We know there's something vast and complex out there, but most of it is hidden from view. This leads to another question. What is dark matter made of? Physicists have spent decades trying to answer that. There are several candidates. One possibility is that dark matter is made up of WIMPs, weakly interacting massive particles. These hypothetical particles are heavy, slow-moving, and interact via gravity, but not electromagnetism, meaning they don't emit light. We've built massive underground detectors to try to catch them, deep beneath mountains, shielded from cosmic rays. But so far, nothing definitive has been found. Another possibility is axions, tiny, ultralight particles that could permeate the universe like a quantum fog. Axions are still theoretical, but physicists are developing clever ways to look for them using magnetic fields and resonant cavities. Then there are sterile neutrinos, primordial black holes, and other exotic possibilities. Some even suggest that dark matter doesn't exist, that perhaps our understanding of gravity is flawed. Maybe we need a new theory of gravity, something that works differently at cosmic scales. This idea, known as MOND, modified Newtonian dynamics, has its own followers and challenges, but none of these theories have yet explained all the data. Dark matter remains one of the most persistent and haunting puzzles in physics. As for dark energy, we understand it even less. Is it a property of space itself, a kind of vacuum energy that arises from quantum fluctuations? Or is it a dynamic field, like a new kind of cosmic fluid? Could it be linked to the cosmological constant that Einstein once introduced and then discarded in his equations of general relativity? He had introduced it to keep the universe static, not knowing that the universe was expanding. But now, it seems the cosmological constant, or something like it, is very real. Some even speculate that dark energy may change over time, that its strength could increase or decrease, and if it increases, it could tear the universe apart. This is known as the Big Rip, a theoretical end scenario where the expansion becomes so rapid that galaxies fly apart, then solar systems, then planets, then atoms themselves. It's a long way off, tens of billions of years if ever. But it's a reminder that we are still at the very beginning of understanding what the universe truly is. And so we come back to the paradox. We understand more about the universe than ever before. We've mapped its galaxies, decoded its radiation, modeled its beginning, and yet we still don't know what most of it is made of. The cosmos, it turns out, is not a place of light, but a sea of shadow, shaped by forces that do not shine. We are creatures of light, trying to understand a universe of darkness. And in that darkness, we are still searching for the particles, the patterns, the explanations that will reveal the invisible threads holding the stars together. Because without dark matter, galaxies would not exist. Without dark energy, the universe would not expand. And without curiosity, we would never ask why. We would simply look at the night sky and think it ends there. But it doesn't. It's only just beginning. Chapter 16, The Ultimate Questions, Before the Bang and Beyond the End. We've travelled far, from the radiant birth of time to the slow expansion of stars and galaxies, to the hidden forces of dark matter and dark energy. We've studied relics of ancient light, uncovered cosmic fingerprints, and followed the subtle warping of space and time. But no matter how much ground we cover, no matter how many theories we explore, there are some questions that seem to hover just beyond our reach. Questions that make us pause, not because they are too complex, but because they may, in some sense, be unanswerable. This is where we arrive at the edge of all scientific understanding and stand face to face with the questions that linger like echoes in the cosmic dark. What came before the Big Bang, and what happens next? These aren't just questions for physicists or astronomers. They are questions that cross the boundary between science and philosophy, between what we can observe and what we can only wonder. Let's begin at the beginning. We've talked about the Big Bang, not as an explosion, but as an expansion of space itself. A swelling of everything from a single, unimaginably dense and hot point. But what was that point? And what, if anything, existed before it? Time itself, according to Einstein's general relativity, began with the Big Bang. Might not even make sense. Still, human curiosity doesn't like blank pages. So scientists and theorists have searched for ways to explore the unknown without breaking the rules of logic or physics. And in doing so, they've proposed some astonishing possibilities. One is the idea of the quantum bounce. In this view, the universe didn't emerge from nothing, but from the collapse of a previous universe. Picture a cosmos that expands, reaches a maximum size, then contracts, pulled back together by gravity, into an incredibly dense state. But instead of collapsing into a singularity and vanishing, the contraction triggers a bounce, leading to a new expansion, a new Big Bang. This is part of what's called loop quantum cosmology, a theory that tries to merge general relativity with quantum physics. In this model, the universe is eternal, not in space, but in cycles. Bounce after bounce, age after age. Another theory is that the Big Bang was the result of a collision, not between objects, but between brains, multidimensional surfaces floating in a higher dimensional space. This idea comes from string theory, which suggests our universe may be just one 3D membrane, or brain among many. When two brains collide, the energy of the impact could create a universe. Ours. In that model, the Big Bang isn't the beginning of everything. It's just the beginning of our universe's observable story. There are even ideas that take us further, into the territory of the multiverse. If inflation, the rapid expansion of space in the earliest moments, is true, it could mean that pockets of space are constantly inflating, forming bubble-like universes. We live in just one bubble, among countless others, each with its own laws, constants, and histories. Some universes might never form stars. Some might be lifeless voids. Others might be eerily similar to ours. And some might be unimaginably alien. This eternal inflation theory suggests that the Big Bang wasn't a unique event, but part of an endless cosmic froth. It's important to note, none of these ideas are proven. They are speculative, theoretical extrapolations, based on the mathematics of physics. We don't yet have a way to test them directly. Maybe we never will. But even asking these questions tells us something important. It tells us that the Big Bang is not the final answer. It's a doorway, a threshold. And on the other side, whatever lies there, could be more extraordinary than anything we've yet imagined. Now let's look the other way. If the Big Bang is the beginning, what is the end? For most of history, the universe was thought to be static, unchanging. Then it was expanding, then accelerating. And now, depending on how we interpret the data, the universe may be heading towards several possible endings, each one shaped by the unseen forces we've only just begun to understand. One possibility is the Big Crunch. In this model, gravity, possibly aided by dark matter, eventually halts the expansion of the universe. Galaxies stop drifting apart. Then, slowly, the expansion reverses. The universe begins to contract. Stars draw closer. Heat rises. Time runs backward in a way. And eventually, everything collapses into a final singularity, like a reverse Big Bang. Another scenario is the Big Freeze, also known as heat death. This is the most widely accepted possibility today. If dark energy continues to drive the expansion of space, galaxies will drift further and further apart. Over billions of years, stars will exhaust their fuel. Black holes will evaporate through Hawking radiation. Matter will decay. And the universe will become a cold, dark, dilute expanse of particles and low-energy radiation, never truly dead, but frozen in time. Then there's the Big Rip. If dark energy is not constant, if it increases over time, then eventually it could tear apart galaxies, stars, planets, even atoms. The fabric of space itself would be ripped apart. All of this sounds distant, and it is. These are events that would occur tens or hundreds of billions of years from now. But the questions matter because they remind us the universe has a history, and that history might have a shape, a rhythm, a fate. And then we reach perhaps the deepest question of all. Why is there something rather than nothing? This question is not just philosophical. Physicists have long wondered why the universe contains anything at all, why matter exists, why space exists, why energy wasn't perfectly balanced by its opposite. After all, if for every particle of matter there was an equal particle of antimatter, they should cancel out. And yet, somehow, matter won. One idea is that during the early moments after the Big Bang, there was a slight asymmetry. One extra particle of matter for every billion pairs of matter and antimatter. When the rest annihilated, that tiny imbalance became everything we see today. You, me, the stars. But why the imbalance? Why that ratio? No one knows. Maybe it was chance. Maybe it was necessity. Maybe there is a principle we have yet to discover, a hidden rule of the cosmic game. And then, of course, there's the greatest mystery of all, consciousness. In a universe born from energy and governed by physics, how did sentient minds emerge? How did atoms and molecules, forged in dying stars, become brains that could look up at the night sky and ask where they came from? This isn't just poetic musing, it's a genuine scientific puzzle. How does matter become mind? How does the universe become aware of itself? Some say consciousness is an emergent property, a byproduct of complex systems. Others believe it may be more fundamental, woven into the very fabric of reality, like space and time. But either way, the fact remains. We are part of this story, not separate, not observers, but participants, born from the same atoms that lit the first stars, built from stardust and silence. And somehow, in the dark spaces between galaxies, we ask questions. We measure light from billions of years ago. We decode particles smaller than atoms. We dream of multiverses and bounce theories off the void. And all of this wonder, this pursuit, is part of what makes the story of the Big Bang more than a scientific tale. It is the human story. It is our story. We find ourselves confronting a boundary that seems to mock our understanding. The moment before the Big Bang. This isn't simply a gap in our knowledge that we might fill with better telescopes or more clever theories. It's something far more fundamental, a place where the very concepts we use to make sense of reality, time, space, causality, existence itself, begin to lose their meaning like words whispered into a vast, empty void. When we ask what came before the Big Bang, we're not just asking about cosmic history. We're asking about the nature of reality itself, about whether the question even makes sense in any meaningful way. Consider what we know with remarkable confidence about the universe's earliest moments. We can trace the cosmic story back to when the universe was less than a second old, when temperatures exceeded billions of degrees and the fundamental forces of nature were unified in ways we can barely comprehend. We have exquisite measurements of the cosmic microwave background radiation, the afterglow of creation itself, that tell us about conditions when the universe was only 380,000 years old. We can observe the abundance of hydrogen and helium throughout the cosmos, perfectly matching predictions from Big Bang nucleosynthesis. We can watch distant galaxies racing away from us, their light stretched and reddened by the expansion of space itself. All of this evidence points to a beginning, a moment when everything we can observe emerged from a state so dense, so hot, so unlike anything in our current universe that it challenges our imagination. The mathematics of general relativity, Einstein's masterpiece that describes gravity as the curvature of spacetime, traces this expansion backward to a point where the equations themselves break down, at what physicists call the Planck time, roughly 10 to the minus 43 seconds after the Big Bang. The very notion of time becomes meaningless. Space and time, those fundamental stages upon which all of physics plays out, simply cease to exist as we understand them. This is where we encounter what might be the ultimate humility. Science, that magnificent tool that has revealed so much about the cosmos, reaches a boundary beyond which it cannot peer. Not because our instruments aren't sensitive enough, not because we haven't been clever enough, but because the concepts that make science possible, measurement, causality, the orderly progression of events in time, may themselves have emerged only with the Big Bang. To ask what came before is perhaps like asking what lies north of the North Pole. The question contains its own impossibility. Yet human curiosity, that restless drive that has carried us from wondering about the lights in the sky to mapping the cosmic web itself, refuses to accept such boundaries without a fight. Theoretical physicists have proposed numerous scenarios for what might have preceded our universe, each more speculative and mind-bending than the last. Perhaps our Big Bang was the result of a quantum fluctuation in some larger multiverse, a brief bubble of space-time that inflated into the cosmos we inhabit. Perhaps it emerged from the collision of higher dimensional objects called brains, whose interaction created not just matter and energy, but the very dimensions in which they could exist. Some theories suggest that our universe might be cyclical, expanding from a Big Bang, eventually contracting in a Big Crunch, only to bounce back in an endless series of cosmic deaths and rebirths. Others propose that what we call the Big Bang was merely a phase transition, like water turning to steam, in some larger structure we can barely conceive. There are models where time itself is emergent, arising from more fundamental timeless quantum processes, and others where our entire universe might be a hologram projected from information encoded on its boundary. Each of these possibilities opens breathtaking vistas of cosmic possibility, while simultaneously highlighting how much we don't know. They're not mere idle speculation. They emerge from serious attempts to extend our best theories beyond their known limits, to push the mathematics of quantum mechanics and general relativity into realms where they've never been tested. Yet they all share a common feature. They push the fundamental mystery back one level without truly resolving it. If our universe emerged from a quantum fluctuation in a larger multiverse, what determined the laws that govern that multiverse? If it arose from colliding brains, what physics governs the higher dimensional space in which those brains exist? Perhaps the most unsettling possibility is that the question itself is fundamentally flawed. When we ask what came before the Big Bang, we're assuming that before has meaning, that causality extends backward beyond the moment when time itself began. But if time is not absolute, if it's not a river flowing from past to future, but rather an emergent property of the universe's expansion, then asking what came before time began is like asking what color the number 7 smells like. The question may be grammatically correct but conceptually meaningless. This doesn't mean we should abandon the quest to understand. The history of science is filled with questions that once seemed impossible to answer. What is matter made of? How do the stars shine? What causes disease? How old is the Earth? Each of these mysteries yielded to patient investigation, clever experiments, and theoretical insights that often required abandoning cherished assumptions about the nature of reality. Perhaps the mystery of what preceded the Big Bang will eventually succumb to some future breakthrough that revolutionizes our understanding as profoundly as quantum mechanics and relativity revolutionized physics in the 20th century. But perhaps it won't. Perhaps we're encountering something deeper than a temporary limit to human knowledge. Perhaps we're glimpsing the edge of what any conceivable intelligence, no matter how advanced, could ever understand about the nature of existence. There may be questions that are not just currently unanswerable, but fundamentally unanswerable. Mysteries that exist at the very heart of reality itself. This possibility, rather than being cause for despair, might actually be a source of profound wonder. In a universe where every question had an answer, where every mystery could eventually be solved, there would be a kind of cosmic claustrophobia, a sense that reality was merely a very large but ultimately finite puzzle, but a universe that contains mysteries that may be intrinsically beyond solution, that harbors questions whose very asking reveals the limits of comprehension. Such a universe retains an element of the truly transcendent. The question of what came before the Big Bang forces us to confront the relationship between scientific knowledge and human meaning. Science has been extraordinarily successful at describing how the universe works, at predicting its behavior, at revealing the elegant mathematical relationships that govern everything from quantum particles to galactic clusters. But it has always been more circumspect about addressing why the universe exists at all, why there is something rather than nothing, why the laws of physics take the particular form they do. These questions touch on deep philosophical and perhaps even spiritual territory. They remind us that for all our scientific sophistication, we remain profoundly mysterious to ourselves. We are arrangements of atoms that have somehow become aware, temporary patterns in the cosmic dance that have learned to contemplate their own existence. We emerged from a universe that was initially devoid of complexity, consciousness, or meaning, yet we have developed the capacity to find beauty in a sunset, to feel wonder at the sight of distant galaxies, to ask questions about our own origins. The mystery of what preceded the Big Bang is intimately connected to the mystery of our own existence. If the universe emerged from nothing, from some quantum vacuum devoid of space and time, then our presence here is perhaps the most extraordinary fact of all. If it emerged from some larger multiverse governed by laws we can barely imagine, then we are participants in a cosmic story whose scope dwarfs even our most ambitious science fiction. Either way, we find ourselves in the remarkable position of being the universe contemplating itself. The carbon in our cells was forged in stellar cores. The calcium in our bones was scattered by supernovae. The iron in our blood was created in the final moments of dying stars. We are not separate from the cosmos, but part of it, temporary arrangements of cosmic matter that have achieved the extraordinary feat of self-awareness. This perspective doesn't answer the question of what came before the Big Bang, but it does suggest that perhaps the question itself is less important than our capacity to ask it. In a universe that began as a featureless soup of elementary particles, the emergence of minds capable of pondering their own origins represents an achievement so improbable, so magnificent, that it defies any simple explanation. We are the universe's way of knowing itself. Cosmic evolution become conscious. The boundary we encounter when we try to peer beyond the Big Bang may be telling us something profound about the nature of existence itself. Perhaps reality is not a problem to be solved, but a mystery to be lived. Perhaps the deepest truths are not equations to be derived, but experiences to be savoured. Perhaps the question of what came before the beginning is less important than the fact that we are here to ask it. In our cosmic journey, we have traced the universe from its earliest moments to the present day, from quantum fluctuations to galaxy clusters, from the first stars to the emergence of life and consciousness. We have seen how gravity sculpted the cosmic web, how stellar fusion created the elements of complexity, how billions of years of evolution gave rise to minds capable of understanding their own cosmic heritage. The story is magnificent in its scope, elegant in its unfolding, and profound in its implications. But perhaps the most remarkable chapter in this cosmic story is the one being written right now, in this moment, as conscious beings scattered across a small planet orbiting an ordinary star in an unremarkable galaxy pause to consider their place in the vast scheme of things. We are the universe become aware of itself. Cosmic evolution reaching a level of complexity where it can contemplate its own existence and wonder about its origins. The question of what came before the Big Bang may ultimately be unanswerable, not because we lack sufficient knowledge or technology, but because it points to something that transcends the very concepts of knowledge and ignorance, existence and non-existence, something and nothing. At this boundary, science reaches its limits not in failure, but in triumph, having carried us to the very edge of what can be known and showing us, with perfect clarity, the mystery that lies beyond. In this mystery, we find not cause for despair, but reason for awe. We inhabit a universe that contains questions bigger than any possible answer, mysteries deeper than any conceivable explanation. This is not a flaw in the cosmic design, but perhaps its greatest feature. In a reality that could be completely comprehended, completely mapped, completely understood, there would be no room for wonder, no space for awe, no possibility for the kind of transcendent experience that comes from standing at the edge of the unknowable. Instead, we find ourselves in a universe that is simultaneously comprehensible and mysterious, knowable and unknowable, familiar and strange. We can trace cosmic history back to its earliest moments and forward to its distant future. Yet we remain baffled by the deepest questions of why there is something rather than nothing, why the laws of physics take the form they do, why consciousness emerges from matter, why we are here at all. These are not problems waiting to be solved, but permanent features of existence, reminders that reality is larger than any mind, no matter how clever, can fully encompass. They invite us not to frustration, but to humility, not to despair, but to wonder. They remind us that we are participants in something magnificent beyond our comprehension, temporary notes in a cosmic symphony whose full score we may never read. As we reach the end of our journey together, perhaps the most appropriate response to the question of what came before the Big Bang is not an answer, but a kind of reverent silence, an acknowledgement that we have been privileged to glimpse, however briefly, the edge of the ultimate mystery. We have traced the universe from its beginning to the present, from simplicity to complexity, from darkness to light, from silence to the emergence of minds capable of asking questions about their own existence. In this asking, in this wondering, in this capacity to stand at the boundary between the known and unknowable, and feel awe rather than frustration, we perhaps touch something essential about what it means to be human, to be conscious, to be alive in a universe that is simultaneously our home and our greatest mystery. The question of what came before the Big Bang may be unanswerable, but our ability to ask it, to wonder about it, to feel both humbled and elevated by its vastness may be among the most remarkable facts in the entire cosmic story. And so we end where we began, with wonder, with questions larger than ourselves, with the recognition that we are part of something magnificent and mysterious that transcends our understanding, while somehow, miraculously, including us within its embrace. The universe may keep its deepest secrets, but it has given us the gift of consciousness, the capacity to wonder, and the privilege of being part of the ongoing story of existence itself. In the end, perhaps that is answer enough. So, what came before the Big Bang? Maybe it was nothing. Maybe it was something beyond our ability to ever understand. Or maybe, just maybe, it was the beginning of a story that has no true beginning. Thanks for spending this quiet journey with me. Wherever you are, may your thoughts be light, your dreams be vast, and your wonder never fade. I hope you have a wonderful and an amazing night. Until next time, stay curious. Keep wondering. This is Boring Science signing off. Cheers.